1. The habitable zone and the cosmic oasis. There is a word that astronomers whisper when they gaze at the cosmos through telescopes and computers that map billions of stars. That word is habitable zone. There was nothing romantic about it at first glance. It's merely a scientific expression, a specific range of distance around a star where the heat is just enough to keep water in its liquid state, not too hot, not too cold. But when you stop and consider what that word truly means, it becomes something profoundly unsettling. The habitable zone is the difference between a planet capable of generating life and one that will remain forever sterile and silent. Earth has orbited within this zone for 4.5 billion years, and that simple location is the first reason why you and I exist, breathing this air. But here's the strange part. Earth doesn't just orbit inside this zone. It orbits at a point so precisely calibrated that it seems almost impossible it happened by chance. Imagine being in an infinite desert under a relentless sun, surrounded by miles of barren sand in every direction. Now, imagine finding a tiny oasis, a green zone of fresh water and abundant life. But it's not any oasis. It's one that, if it were just 5% closer to the scorching sun, would dry up forever. And if it were 10% farther away, it would freeze. Earth is that cosmic oasis, that impossible zone of perfection that must exist in a very specific place to work. Billions of planets have been discovered around other stars in the past 20 years, a number once inconceivable. Astronomers expected to find many worlds like Earth, rocky planets orbiting within habitable zones around their stars. They found some, but the proportion is devastatingly small. Only about 5% of identified exoplanets are even within the correct habitable zone. And of those few, most lack the additional characteristics Earth possesses to sustain complex life. When you think about existence, how we came to be, the first condition is being in the right place. Earth is in the right place, orbiting at the perfect distance from the sun, within a temperature range that allows liquid water, in a position that no other planet in our system shares. The development of this idea in modern science truly began at the end of the 20th century, when astronomers started to ask themselves a simple but profound question. If there are other suns, do they have planets? For decades that remained pure speculation. We could not see those distant worlds. But in 1992, astronomers Alexander Wolszczan and Dale Frail made a discovery that would change everything. They detected the first exoplanets around the pulsar star PSR 1257+12. They weren't planets orbiting a sun-like star, but the discovery proved that our solar system wasn't unique. Later, in 1995, Michel Mayor and Didier Queloz discovered 51 Pegasi b, a planet around a star similar to the Sun. That discovery was the spark of a revolution. Suddenly, the universe was full of planetary systems, billions of them. But as astronomers mapped these worlds, a troubling reality emerged. Most of these planets weren't in the habitable zone. There were hot gas giants in scorchingly close orbits to their stars, frozen worlds at the edge of intergalactic nothingness, and a few theoretically inhabitable zones, but lacking the orbital configurations Earth has. Earth isn't just in the right zone. It's in a zone that seems to have been arranged with invisible cosmic care. Its orbit is almost perfectly circular, not overly elliptical. If it were more elliptical, it would experience extreme temperature variations that would make the already difficult seasons unbearable. Its axial tilt is 23.5 degrees, a tilt that creates moderate seasons and a reasonable distribution of heat between hemispheres. Its distance from the Sun is 150 million kilometers, a distance so specific that astronomers call it one astronomical unit. Every measurement of habitability in other systems is compared with this distance. Other planets in other systems may be technically in habitable zones, but often barely. Earth sits comfortably nestled at the heart of this zone, as if protected by an invisible bubble. And this bubble of habitability does not exist by accident.
When we reflect on what this means, we're confronted with a deep truth. Earth's habitability isn't merely an accidental fact. It's part of a larger pattern, a grander system, a cosmic orchestration anchored in mathematics and physics. Scientists who study exoplanetary systems now know that for a planet to be habitable, it isn't enough to be in a temperature-suitable zone. It must have proper composition, magnetic fields, stable atmospheres, protection from stellar radiation, and, perhaps most importantly, other planets that should never be ignored. The habitable zone is not just a matter of distance from the Sun. It's a matter of being in a system where everything conspires, together, to keep that planet safe, stable, and alive. Right now, you sit comfortably breathing on a planet that's in a place so special that billions of other worlds will never achieve it. And that location is only the beginning of the story of why Earth is strange, why it is special, why you exist. The next facts will peel back the layers of this protection, showing that the habitable zone is not the only factor. There are many other silent guardians, many other cosmic conspirators that worked together to keep this small blue bubble alive.
2. The miracle of liquid water. Water is strange. If you look at any chemistry book, you'll be surprised by how many abnormal properties water has compared to other simple molecules. It should be a gas at room temperature, and in fact, it's only by a kind of molecular miracle that it exists as a liquid on Earth. Water is an anomaly, an exception, a molecular marvel that manages to remain liquid where, according to the statistical laws of chemistry, it shouldn't. Imagine a molecule of its size and specific weight under normal conditions. It would be a gas. Other similar molecules, such as ammonia or hydrogen sulfide, behave as gases at room temperature. But water? Water flows. Water runs. Water fills our oceans, and it's precisely for that reason that life exists. Without liquid water, there would be no complex chemistry. Without chemistry, no organic molecules. Without organic molecules, no life. All biology as we know it, from the tiniest bacteria to the tallest trees and flying skies, is based on water. When astronomers search for life on other worlds, the first question they ask is there water? Not because water is the only possible basis for life, but because it is extraordinarily good at being a solvent, dissolving molecules, enabling complex chemical reactions. So any alternative version of life seems statistically improbable. Thus we have this cosmic situation. A planet must not only be in the right temperature zone, but must also possess abundant amounts of water. And that water must exist in liquid form, not vapor, not ice. Liquid. Earth has 3 oceans covering 71% of its surface. There is fresh water in lakes and rivers, frozen water at the poles. Water is everywhere, so ubiquitous that it's easy to forget how rare it is. At this very moment, there are about 1.386 billion cubic kilometers of water on the planet, a number so large it defies comprehension. Yet across the entire Milky Way galaxy, among billions of stellar systems, liquid water in abundant quantity is astonishingly rare. The history of water on Earth is a story of cosmic luck that defies simple explanation. When the solar system began forming 4.6 billion years ago, the region near the Sun was too hot for liquid water. The materials that formed Mercury, Venus, and Earth consisted mainly of silicates and metals. But water, billions of trillions of tons of it, was everywhere in the early solar system, locked within comets and asteroids in the colder regions beyond Mars's orbit. The question astronomers asked was, how did all that water reach Earth? The answer remained a mystery until recently. Scientists once suggested that water-rich comets bombarded the young Earth, delivering the precious molecule. But there was a problem. The isotopic composition of water in comets didn't match perfectly with that of Earth's oceans. Then, In 2015, astronomers using data from the Herschel telescope discovered a more intriguing answer. Earth's water came from much closer asteroids, ones orbiting in the region where Mars formed. These asteroids were transported to the young Earth by gravitational disturbances caused by, you guessed it, other planets. Studies point especially to Jupiter as the key driver of that transfer. Its immense gravity pushed and pulled asteroid systems, and some of those water-rich asteroids were directed toward Earth's orbit. Without Jupiter's presence, without its gravity shaping the early planetary system, this transfer of water might have happened differently, or not at all. But there's more. It wasn't just about getting water. It was about getting the right amount of it. Too much water, and Earth would be a complete ocean world with no dry land for complex life to evolve. Too little, and there wouldn't be enough for the global ecosystems we know. Earth has precisely the right quantity, enough to cover 71% of its surface, while leaving 29% as solid land. That proportion is no accident. The significance of this reality is profound. Life as we know it doesn't just require a planet to be in the habitable zone. It requires that planet to receive water from specific cosmic sources in precisely calibrated amounts through processes that depend on other planets, celestial bodies that never touch Earth, orbiting in regions no human has ever visited. Life on Earth is, essentially, a product not only of this blue bubble, but of an entire cosmic system working in perfect synchronization. When you drink a glass of water at this moment, that water carries a history dating back to asteroids that once turned in their orbits billions of years ago. Specific molecules in your oceans may have been delivered by comets traveling through the vacuum of space. And all of that happened because Jupiter, a planet you can see at night as a bright point in the sky, a world you'll never touch, organized the solar system so that water could arrive here in the exact quantity and form necessary for life to exist. Water is not just a strange molecule. It's the reason you exist. 3. Earth's atmosphere as an invisible shield. There is an invisible layer around you right now. It isn't magical. It isn't supernatural. It's simply the atmosphere, a mixture of gases that wraps Earth in a shell so thin and delicate that if represented on a 1-meter globe, it would be thinner than a sheet of paper. This layer is so transparent, you completely ignore it. You breathe it. Light passes through it. Sound travels through it. But this invisible layer may be the most crucial shield between life on Earth and the deadly vacuum of space. Earth's atmosphere is composed mainly of nitrogen, 78%, and oxygen, 21%, with small amounts of argon, carbon dioxide, water vapor, and other trace gases. But it's not just the composition that matters, it's the pressure. The atmospheric pressure at Earth's surface is about 1 atmosphere, or 101,325 pascals. That means the weight of the entire atmosphere above you is pressing down with roughly 1 kilogram per square centimeter. You don't feel it because every part of your body is under equal pressure. But if that pressure were significantly different, higher or lower, life as we know it could not exist. If it were much lower, water would boil at much colder temperatures. If much higher, the chemistry of life would be altered in disabling ways. Earth's atmosphere not only allows breathing, it allows water to remain in its preferred state, enables chemical reactions to occur at proper speeds, and lets global temperature vary within a narrow, stable range. But here's the really strange part. This atmosphere isn't static. It's under constant attack. Radiation from space strikes it. Charged particles from the solar wind try to penetrate it. The atmosphere is continually regenerated through biological and geological processes, and its stability depends directly on other planets. How did the atmosphere come to be this way? The story takes us back 4 billion years, when early Earth was a completely different world. The original atmosphere was mostly nitrogen, but also contained carbon dioxide, ammonia, water vapor, and methane. There was no free oxygen, only trace amounts.
This atmosphere was produced mainly by volcanic degassing, geological processes that released gases trapped inside Earth. Then, something extraordinary happened about 3.5 billion years ago. The first photosynthetic organisms, cyanobacteria and archaea, began photosynthesis. They absorbed carbon dioxide and water, releasing oxygen as waste. Billions of these microorganisms did so for hundreds of millions of years, slowly increasing atmospheric oxygen. This was the Great Oxidation Event, one of the most transformative events in Earth's history. Why does this matter for understanding how planets help each other? Because the process that allowed this atmospheric transformation was deeply influenced by planetary dynamics. Earth's orbital stability, dependent on Jupiter and other planets, allowed life to persist long enough to evolve photosynthesis. Without that stability, without that cosmic guardianship, the atmosphere would never have changed. Life would not have multiplied. Oxygen would not exist. Moreover, Earth's specific atmospheric composition is also protected by forces involving the solar system's entire magnetic structure. Earth's magnetic field, discussed next, shields the atmosphere from solar radiation. But even that magnetic field is influenced by the solar wind and magnetic patterns shaped by the Sun and other planets. The deep truth is that the atmosphere is both a product and a protector. It's created by the biological and geological processes of Earth, but maintained and stabilized by factors far beyond it. Astronomers studying Mars, for example, see what happens when an atmosphere is unprotected. Mars once had one. Billions of years ago, it had liquid water, rain, perhaps even primitive life. But Mars is smaller than Earth, with weaker gravity. Its core cooled faster. Its magnetic field died. And once unprotected, its atmosphere was slowly stripped away by the solar wind. Over billions of years, Mars's atmosphere simply evaporated into space. Today, its air is so thin, it's lethal. Atmospheric pressure less than 1% of Earth's. Liquid water cannot exist there because the pressure is so low that water boils at near freezing temperatures. Complex life is impossible. When you breathe this invisible air, when you feel the soft pressure of the world around you, you are experiencing something Mars no longer has. You are breathing the grace of the solar system. And that grace is no accident. It's the result of Jupiter keeping Earth stable, the result of the Sun creating a solar wind Earth learned to resist, and the result of billions of years of cosmic processes that conspired to keep you alive. 4. Earth's magnetic field, silent protector. There is a shield around you that you never see. It isn't a wall. It isn't made of stone or metal or any tangible material. It's made of invisible magnetic fields, stretching tens of thousands of kilometers into space. If you could see it, it would look like a magnetic halo, a bubble of magnetic force enveloping Earth and its atmosphere. Astronomers call this region the magnetosphere, and it's so important to Earth's life that without it, none of us would exist. Earth's magnetic field is generated by processes deep within its core. The inner core is solid, composed mainly of iron at temperatures reaching 5,200 degrees Celsius, hotter than the surface of the Sun. Surrounding it lies the outer core, a liquid layer of molten iron and nickel. As Earth rotates, this liquid metal moves, and when conducting metals move, they create magnetic fields. It's the same principle behind a copper wire generating electricity when it spins in a magnetic field. Earth's core is a planet-scale generator. Its geodynamo, as scientists call it, has functioned for billions of years, producing a magnetic field that extends far into space. This field isn't uniform or constant. It follows a pattern like that of a bar magnet, with north and south poles. Magnetic field lines emerge from the South Pole, curve around the planet, and re-enter at the North Pole. Every compass needle tries to align with these invisible lines of force. But why does this matter for life? Because the Sun is far less calm than it seems. The solar wind, a continuous stream of charged particles from the sun, blows plasma at around 400 kilometers per second. If these particles hit Earth directly, they would devastate the atmosphere, destroying ozone molecules that shield against ultraviolet radiation and damaging the DNA of organisms on the surface. Over billions of years, the solar wind would strip the atmosphere away, just as it did to Mars. But Earth has a protector. Its magnetic field deflects those particles. When the solar wind approaches, it meets Earth's magnetic lines and is diverted. Most pass harmlessly around the planet. Some get trapped in zones called the Van Allen radiation belts, huge dome-like regions above the equator where charged particles remain confined by the field. The magnetic field doesn't just protect us, it keeps us alive. In 2003, astronomers observed a particularly violent solar storm striking Earth's magnetosphere. The storm was strong enough to damage satellites, disrupt communications, and induce electric currents across entire continents. Without the magnetosphere, this storm would have stripped away part of our atmosphere, exposing life to lethal radiation. The field kept us safe. Now, here's how it all connects. Earth's magnetic field exists because the planet has a molten iron core. But why does Earth have such a hot, energetic core? Because Earth is massive enough to retain heat from its
formation and from radioactive decay within. And why is Earth massive enough? Because in its early history, it accumulated material through collisions with asteroids and planetary embryos. Collisions governed and moderated by the gravity of Jupiter and other giant planets. If Jupiter's orbit had been different, Earth would have accumulated a different amount of material, formed a different core, perhaps no magnetic field at all. Without a magnetic field, complex life would never have evolved. There's another layer of meaning when you reflect on this. Earth's magnetic field isn't constant. Periodically, on average every 450,000 years, though irregularly, it reverses. The magnetic north becomes south, and vice versa. During these reversals, the field weakens, sometimes to just 10% of its usual strength. When that happens, protection against solar wind diminishes dramatically, and Earth receives higher doses of radiation. The auroras spread farther. Living organisms experience slightly higher radiation exposure. It's not enough to destroy life, but enough to leave a mark. Paleontologists have found the imprints of magnetic reversals in ancient geological sediments, patterns of radiation matching times when the field was weaker. Life on Earth evolved to endure these reversals. It learned to tolerate brief surges in radiation. Organisms developed more efficient DNA repair mechanisms. Life evolved colors and body structures that provided better protection. All this happened because, even in its weakest moments, Earth's magnetic field remains always there, still shielding, still deflecting most of the destructive solar wind. You sleep beneath an unseen shield. And that shield exists because Earth was born in a solar system where other planets conspired to make it just the right size, with just the right internal heat, capable of generating the invisible protector that lets life breathe. 5. The moon and tides, the invisible guardian. Imagine standing by an ocean, watching the tide pull back from the shore. Water that moments before covered the sand now retreats, revealing rocks and creatures of the shallow seabed. Then, hours later, it returns, climbing higher than before, erasing the landscape that was just exposed. This rhythm has been repeating for billions of years, day after day, tide after tide, a silent pulse that shapes coastlines and regulates the life that dwells within them. Most people think of tides as a simple consequence of the moon's gravity, and this is true, but what they fail to realize is that without the moon, without its specific size and its precise distance from Earth, tides would either not exist or would be so weak that the chemistry of life itself would change fundamentally.
The Moon orbits at approximately 384,400 kilometers from Earth. That distance is not random. It is precisely calibrated to create tides of the right magnitude. When the Moon's gravity pulls on Earth's oceans, it does not pull them uniformly. The side of Earth facing the Moon experiences stronger gravitational attraction than the opposite side. This difference creates a bulge of water facing the Moon and another bulge on the far side of the planet, both pushed outward by this differential force. As Earth rotates, different regions move through these bulges, creating 2 high tides and 2 low tides each day. The tides regulate ocean currents. These currents distribute heat around the planet. Without tidal mixing, warm equatorial water would remain at the equator, and cold polar water would remain trapped at the poles. Life would be distributed unevenly across the planet, flourishing in some regions and remaining impossible in others. But the tides stir the oceans like an invisible hand, ensuring that nutrients from deep waters are brought to the surface, where sunlight penetrates and life feeds. Organisms in the tidal zones, the areas that are alternately covered and exposed by the changing waters, have evolved some of the most remarkable adaptations in biology. Starfish that can survive hours without water, algae that withstand both desiccation and being fully submerged, crustaceans with shells that can resist enormous pressure changes. These creatures exist because the Moon creates the tidal zones through its constant gravitational embrace. If the Moon were much closer, the tides would be catastrophically large. Coastal cities would be washed away by surges many meters high. If the Moon were farther away, the tides would be so weak that the oceans would become stagnant, and life as we know it would suffocate. The Moon exists at precisely the right distance to create tides that are vigorous enough to stir the oceans, but not so violent as to destroy the biosphere. But here is where the story becomes truly strange, because the Moon should not be where it is. The current theory of the Moon's origin is that 4.5 billion years ago, a
Mars-sized object called Theia collided with the young Earth at a glancing angle. The impact was cataclysmic. Huge amounts of material from both Earth and Theia were vaporized and ejected into space. From this debris disk orbiting the Earth, the Moon coalesced. This event is called the Giant Impact Hypothesis, and it explains many features of both Earth and the Moon. But the odds of this collision happening are extraordinarily low. The probability that a Mars-sized body would strike Earth at just the right angle to create a Moon of the right size and at the right orbital distance is so small that it borders on miraculous. If Theia had been slightly larger, the Moon would have been captured into a much closer orbit, or might have been destroyed entirely. If it had been smaller, the Moon would have drifted away or never formed at all. If the angle of collision had been different, the Moon might have ended up on an elliptical orbit far from Earth, creating unpredictable and catastrophic tides. But it did not. The Moon formed in the exact orbital configuration needed for life to thrive. Scientists think they understand why. The giant impact did occur, but it was not entirely random. In the early solar system, many planetary embryos orbited the young Sun, competing for space and material. The gravitational interactions between these embryos were complex and chaotic. Some embryos were ejected from the inner solar system, others collided with planets already formed. Theia's collision with Earth was therefore not an accident in the sense of being purely random. It was a nearly inevitable consequence of the violent dynamics of the early solar system, dynamics that were themselves shaped by the presence of the giant planets, especially Jupiter. Jupiter's gravity influenced the orbits of the planetary embryos. It stirred the inner solar system, creating a chaotic dance of collisions that eventually settled into the planetary system we see today. Without Jupiter, without its specific mass and its specific orbit, the chain of events leading to the Moon's formation might never have occurred. Or if it did, it might have produced a different Moon at a different orbital distance, with different consequences for the evolution of life on Earth. The Moon moves away from Earth at a rate of about 3.8 centimeters per year. This has been measured with astonishing precision, using retroreflectors left on the lunar surface by Apollo astronauts. The Moon is escaping Earth's gravitational embrace, not catastrophically, but slowly, inexorably, year after year. In the distant past, the Moon was much closer. 3 billion years ago, the Moon orbited Earth at a distance of perhaps 20,000 kilometers, instead of the current 384,000 kilometers. At that distance, the tides would have been immense, perhaps as much as 1,000 meters high. The oceans would have been in constant turmoil. Yet those violent tides may have been essential for life's early evolution. The tidal mixing in ancient oceans would have been extraordinary, bringing nutrients from the deep to the surface with tremendous force. The tidal energy would have heated the oceans slightly, providing thermal gradients that primitive chemistry could exploit. Some scientists propose that the earliest chemical reactions that led to life may have taken advantage of tidal energy. If this is true, then life itself was cradled in the violent tides, created by a much closer Moon. Billions of years passed, and the Moon slowly receded. The tides gradually weakened. Over time, the oceans settled into patterns that allowed complex life to flourish. The moment when the Moon achieved its current distance, approximately the moment when it reached approximately its current orbital configuration, coincided with the emergence of the first complex multicellular organisms. The timing may be coincidence, or it may reflect a deep connection between the Moon's gravity and the conditions necessary for life's evolution. When you stand by the ocean and watch the tide retreat, you are witnessing one of the most profound expressions of cosmic connection on Earth. The water moves not because of wind or weather, but because a celestial body, 384,000 kilometers away, exerts a gravitational pull so precisely calibrated that it creates rhythms of life in the oceans. The Moon does more than create tides, though. It stabilizes Earth's axial tilt. Earth's axis is inclined at 23.5 degrees relative to its orbital plane. This inclination creates the seasons. The tilt toward the Sun produces summer in one hemisphere, while the other experiences winter. Without this tilt, Earth would have no seasons. The equator would receive more energy from the Sun than the poles, and heat would distribute very unevenly. Climate would be harsher, less stable, and the diversity of life would be reduced. But the axial tilt does not remain constant. The Moon's gravity exerts a torque on Earth's equator, preventing the tilt from precessing too wildly. Other planets in the solar system, those without large moons, experience much larger variations in their axial tilt over geologically short timescales. Without the Moon, Earth's axial tilt could vary from almost 0 degrees to more than 60 degrees over periods of millions of years. Such variations would produce climate chaos, ice ages in the tropics, tropical heat at the poles. Life would be driven to extinction repeatedly. The fact that Earth maintains a relatively stable axial tilt is directly attributable to the Moon's presence. The Moon stabilizes the climate. With the Moon present, the seasonal patterns remain predictable. Life has had time to evolve into complex forms, to develop strategies for surviving and thriving through the predictable seasons. Without the Moon, Earth would be a world of extreme and unpredictable climate fluctuations, a world far less suitable for the development of complex life. The presence of the Moon at the right orbital distance, with the right mass, creating tides of the right magnitude while stabilizing the axial tilt of exactly the right angle. All of this seems too perfect to be accidental. And yet, it all flows from the giant impact, an event so improbable that its occurrence seems to defy calculation. But this is the pattern that emerges when we look at Earth's habitability. Each factor, the distance from the Sun, the composition of the atmosphere, the presence of a protective magnetic field, the location in a system of planets that organize the dance of bodies, each factor was influenced by the presence of other planets. Each factor points back to a hidden orchestration, a coordination between celestial bodies that seems almost intentional. The Moon is the most visible expression of this orchestration. When you see the Moon in the night sky, you are looking at a body that billions of years ago was born from a collision shaped by the gravitational influence of Jupiter. You are looking at a guardian that maintains the conditions necessary for your existence. Every tide that moves through the oceans, every stable season that allows crops to grow, every predictable climate that permits civilizations to flourish, all of this rests on the Moon's presence. And the Moon exists because the entire solar system conspired through the medium of physics and gravity to create it. 6. Venus as mirror of destiny. Imagine a world that mirrors Earth in many fundamental ways. A terrestrial planet orbiting a star, bathed in the same stellar radiation, composed of similar rocky materials. A world that should be habitable. And yet, when you arrive at this world, you find a hellscape beyond imagination, a surface temperature of 465 degrees Celsius, an atmosphere of carbon dioxide so thick that the atmospheric pressure on the surface is 92 times greater than Earth's atmospheric pressure at sea level. Clouds of sulfuric acid that completely obscure the surface. A world where lead would melt on the ground. This is Venus, and it exists in the same solar system as Earth, orbiting only slightly closer to the Sun. The comparison between Venus and Earth is one of the most important lessons in planetary habitability. It shows what can happen to a world when conditions are not quite right. It reveals the fragility of habitability. It demonstrates that Earth is not merely in a habitable zone, but is in a very specific and narrow range of conditions within that zone. Venus orbits at an average distance of 108 million kilometers from the Sun, compared to Earth's 150 million kilometers. This difference in distance, a mere 28% closer to the Sun than Earth, has catastrophic consequences. The solar radiation at Venus is about twice as intense as at Earth. This increased radiation heats Venus's atmosphere and surface far more intensely. But the problem goes deeper than simple heating. What scientists believe happened is this. In Venus's early history, approximately 4.5 to 3 billion years ago, Venus may have been much more like Earth. It may have had liquid water oceans on its surface. It may have had a thinner atmosphere. The early Sun was dimmer than it is today, about 25 to 30% dimmer. So even though Venus was closer to the Sun, it may have received a similar amount of radiation to what Earth receives today. Under those conditions, Venus could have developed a carbon dioxide atmosphere, much like Earth, with water vapor in the air and liquid oceans at the surface. Ultraviolet radiation from the Sun would have broken down water vapor molecules in the upper atmosphere, releasing hydrogen, which would have escaped to space. Oxygen would have combined with rocks on the surface and been buried. The result would have been a progressive loss of the water that originally covered Venus. As the Sun warmed over billions of years, as its output of radiation increased according to the normal evolutionary path of stars, Venus's surface temperature would have risen. The hotter the surface became, the more water vapor would evaporate from the oceans. Water vapor is a powerful greenhouse gas. As more water vapor accumulated in the atmosphere, it trapped more heat, causing the temperature to rise further. This created a runaway greenhouse effect, a feedback loop that fed on itself. The oceans evaporated completely. The atmosphere became
dominated by carbon dioxide from the outgassing of rocks. And the planet entered a state of extreme heat that has persisted to this day. This scenario is called the wet Venus hypothesis, though it remains controversial among planetary scientists. Some models suggest that Venus may never have had significant water oceans. But whether Venus once had oceans or not, the key insight remains. Venus shows what happens to a terrestrial planet when the balance tips toward a runaway greenhouse effect. If Earth were just 5% closer to the Sun, our planet would receive enough additional solar radiation to trigger a runaway greenhouse effect. Our oceans would evaporate. A thick carbon dioxide atmosphere would form. Earth would become Venus. The fact that Earth is not Venus, that we remain in a state with liquid oceans and a relatively thin atmosphere, is therefore a matter of precise positioning. The difference between habitability and hellscape is the difference between 150 million kilometers and 160 million kilometers from the Sun. A difference of just 10 million kilometers out of 150 million, or about 6%. This is the margin by which Earth avoids the fate of Venus. What determines where a planet forms in the solar system? Why does Earth orbit at 150 million kilometers and Venus at 108 million kilometers? The answer lies in the dynamics of planetary formation. When the solar system was forming, planetesimals, small bodies composed of rock and ice, orbited in a disk around the young Sun. These planetesimals collided with each other, coalescing into larger bodies. The bodies in the inner solar system were warmer, so water and other volatile compounds could not condense into solids. Only rocky materials remained. In the outer regions, farther from the Sun, the temperature was cold enough for water ice and other ices to remain solid. This created a dividing line called the snow line, or frost line. Planets forming closer than the snow line were rocky worlds. Planets forming farther than the snow line could accumulate large amounts of ice and become gas giants if they were massive enough. The position of the snow line is determined by the temperature of the solar nebula, which is primarily determined by the distance from the Sun. But the snow line's position can also be influenced by the dynamical interactions of growing planets. Jupiter, forming beyond the snow line, was able to accumulate enormous amounts of material and grow into a gas giant. Jupiter's formation and the accumulation of its mass were not isolated events. They influenced the orbits of planetesimals throughout the solar system. The gravitational influence of Jupiter and Saturn, then young and still in the process of forming, stirred the orbital dynamics of the inner solar system. The theories of planetary migration suggest that Jupiter may have first migrated inward, bringing gravitational chaos to the inner solar system, before migrating back outward. This migration would have influenced the formation and orbital positions of the terrestrial planets. Earth formed where it did, at 150 million kilometers, as a result of this complex dynamical history. Venus formed at 108 million kilometers. Had Jupiter migrated differently, had its orbit been different, had its mass been slightly different, the positions of Venus and Earth might have been reversed. Earth might have been the hellscape, and some other world, the Oasis. The current positioning is therefore not inevitable. It is the result of a specific orbital history, shaped by the presence and dynamics of the giant planets. When you consider the habitability of Earth, you cannot separate it from the presence and configuration of the other planets in the solar system. Earth is habitable not only because of its own properties, but because it orbits at a distance from the Sun that is just far enough to avoid the Venus runaway effect, but close enough to receive the solar radiation needed to support liquid water and life. This positioning is fragile. It is a knife edge between hellscape and paradise. And it was achieved through the orbital dance of the giant planets in the young solar system. Every time the Sun appears on the horizon, filling the sky with light and warmth, remember that you are seeing light that strikes Earth at precisely the right intensity to create and sustain life. You are not seeing the light of a generic star with a generic planet. You are seeing the light that results from a specific chain of cosmic events. From Jupiter's migration, from Venus's formation at its particular orbital distance, from Earth's formation at its particular orbital distance, from the cumulative effect of gravitational interactions between multiple planetary bodies over billions of years. Venus is not just a dead world. It is a warning. It is a mirror that reflects what Earth could become if the conditions were slightly different. It is a reminder that habitability is not guaranteed. It is contingent on a precise alignment of factors. And when you realize that these factors were shaped by the presence of other planets, by Jupiter, by Saturn, by Mars, you begin to see Earth's habitability not as the inevitable result of physical law, but as an improbable gift. A world maintained by the invisible choreography of planets dancing to the rhythm of gravity across billions of years.
7. Mercury and Mars, the extreme didactics.
If Venus teaches us what happens when a world is too close to the Sun, Mercury and Mars teach us the equally important lessons of what happens at the extreme ends of planetary habitability. Each in their own way, they define the boundaries of the habitable zone. They show us the limits beyond which complex life cannot flourish. Mercury orbits at an average distance of 57.9 million kilometers from the Sun, closer than any other planet. It is a small world, only slightly larger than Earth's moon. Its orbit is highly elliptical, so it swings between 46.0 million kilometers at its closest approach to 69.8 million kilometers at its farthest. The temperature variation is extreme. On the sunlit side, facing the Sun directly, the surface temperature reaches approximately 430 degrees Celsius. On the dark side, facing away from the Sun into the depths of space, the temperature plummets to approximately minus 170 degrees Celsius. Mercury rotates very slowly. One rotation takes 59 Earth days. It also orbits the Sun with a period of 88 Earth days. Because of this unusual relationship between rotation and orbital period, a phenomenon called tidal locking, Mercury always presents the same face, more or less, toward the Sun. This creates the extreme temperature contrasts. The sunlit side is relentlessly hot. The dark side is profoundly cold. No liquid water can exist on the surface, no atmosphere to moderate the temperature or carry heat from dayside to nightside. Mercury is essentially sterile. It is too hot, too small, too close to the Sun. It lost its atmosphere to the solar wind. It lost any water it might have had to evaporation or chemical reactions with hot rock. Mercury shows us one extreme. Mars shows us another. Mars orbits at an average distance of 227.9 million kilometers from the Sun, farther than Earth's 150 million kilometers. Mars is smaller than Earth, about half the size. Its atmosphere is thin, less than 1% of Earth's atmospheric pressure. The atmospheric composition is dominated by carbon dioxide, with traces of nitrogen and argon. The surface temperature averages about minus 65 degrees Celsius, though it can reach minus 125 degrees Celsius in the polar regions. Water exists on Mars, but primarily as ice at the poles and frozen into the regolith. Liquid water may exist briefly on the surface or in subsurface aquifers, but it cannot persist in large quantities on the current Martian surface. Mars was not always this way. Evidence from orbital spacecraft and rovers suggests that Mars once had a thicker atmosphere, warmer temperatures, and liquid water flowing on the surface. Geological features, such as dried riverbeds and minerals that form only in water, suggest that Mars may have had habitable conditions billions of years ago. But something changed. Mars became cold. The atmosphere thinned. The water disappeared. Why? The leading theory is that Mars is too small to sustain a
Planetary magnetic field over geological timescales. The core of Mars has cooled over billions of years. Without an active molten core, the planetary magnetic field weakened and eventually shut down. Without the magnetic field to protect it,
Mars's atmosphere was gradually eroded away by the solar wind. High-energy particles from the Sun struck the atmosphere, imparting enough energy to accelerate atmospheric atoms and molecules beyond escape velocity. Over billions of years, the atmosphere was stripped away into space. As the atmosphere thinned, the greenhouse effect weakened. The planet cooled further. Liquid water became impossible to maintain. Mars became the cold, dry, largely lifeless world we see today. Mars teaches us a crucial lesson. A planet must be large enough to maintain a molten core, and therefore a magnetic field. A planet must be massive enough to retain an atmosphere against the assault of the solar wind. Earth is larger than Mars. Earth's core remains molten. Earth's magnetic field remains active. Earth can retain its atmosphere. Mars cannot. If Earth were Mars-sized, we would have suffered the same fate. The habitability of Earth is therefore dependent not only on its position relative to the Sun, but on its mass, its size, its interior composition, the presence of a molten core and an active magnetic field. All of these are consequences of events in the early solar system. The collision with Theia that created the Moon, the distribution of planetary mass, the orbital dynamics that brought material to Earth and away from Mars. When we look at Mercury and Mars, we are looking at the boundaries of habitability. We are looking at what becomes of planets that are too hot, too small, too close, or too cold. We are looking at the negative space around Earth, the void where life cannot flourish. Earth rests between them, not too hot like Mercury, not too cold like Mars, large enough to retain an atmosphere and maintain a magnetic field, positioned in the solar system where the right amount of solar radiation reaches the surface. The margins are smaller than most people realize. The habitable zone extends from roughly 0.95 AU to 1.37 AU from the Sun, where an AU, astronomical unit, is the distance from Earth to the Sun. Earth at 1.0 AU is near the inner edge of this zone. Venus at 0.72 AU is too close. Mars at 1.52 AU is near the outer edge, but its size makes it uninhabitable, even though its orbit is within the habitable zone. When you stand on Earth and look up at the night sky, you are standing on a world distinguished by its position, its mass, its internal composition, and its magnetic field. You are standing on a world that should be extraordinarily rare. Mercury and Mars are reminders of why. They show the fates that awaited Earth if any one of several factors had been slightly different. They define the narrow corridor in which Earth exists, a corridor sculpted not by accident, but by the gravitational choreography of the planets and the early bombardment that shaped the solar system's architecture. 8. The perfect interval. Transition to exploration. We are now reaching a threshold. We have explored the foundational concepts of habitability, the habitable zone, the necessity of liquid water, the protective atmosphere, the magnetic field, the stabilizing moon. We have looked at what becomes of worlds at the extremes: Venus, burning and runaway greenhouse chaos; Mercury, scorched and frozen by its proximity to the Sun; Mars, losing its protective shield to the solar wind; and we have seen Earth, resting in an improbable middle ground. All of this is true. All of this describes essential conditions for life. But now we must go deeper. We must answer a question that has been present throughout this discussion, but not yet explicitly stated. How did Earth come to be in this middle ground? Why is Earth positioned so precisely at the boundary of habitability? Not too hot, not too cold, but in the exact range where liquid water can exist. Why does Earth have the size, the composition, the internal heat that generates a magnetic field? Why does Earth possess a moon with the exact mass and orbital distance necessary to stabilize the climate and regulate the tides?
Coincidence? Perhaps. But as we begin to look at the other planets in the solar system, as we begin to examine their roles in maintaining Earth's habitability, we will find that coincidence seems an increasingly inadequate explanation. The first four facts have painted a portrait of Earth's habitability in isolation, conditions that exist on Earth and are necessary for life. But Earth does not exist in isolation. It exists within a system of 8 planets, dozens of moons, millions of asteroids, and 1 star. And the habitability of Earth is not a property of Earth alone. It is a property of the system. It emerges from the interactions between the planets. The planetary system is like an orchestra. Each instrument plays a different note, produces a different sound, but the beauty of the orchestra emerges not from any single instrument, but from how the instruments interact, how they harmonize, how the tones combine and reinforce each other, and how the conductor, in this case, the laws of physics and gravity, orchestrates their relationships. Without all the instruments, there is no symphony. There is only noise. And so too with the solar system. Earth is one instrument. But Earth's habitability is not produced by Earth alone. It is produced by Earth playing in harmony with the other planets. The following facts will explore this harmony. We will look at Jupiter's role as a cosmic shield. We will examine Saturn's complementary protection. We will consider how Mars and Venus and Mercury define the boundaries beyond which the habitable zone cannot extend. And we will begin to understand that Earth's inhabitability is not an accident. It is the result of a vast and invisible choreography, a dance of planets that has been performing for 4.6 billion years. A dance that has been
perfectly preserved to allow life to flourish. What we are about to discover is this. The other planets are not merely distant bodies. They are active participants in maintaining Earth's habitability. They are guardians, protectors, silent orchestrators of the conditions that allow us to exist. To prepare yourself for this discovery, it is worth pausing to reflect on what we have already learned. In just the first 8 facts, we have learnt that to sustain life, a planet must be positioned at a specific distance from its star. It must have liquid water. It must have a protective atmosphere. It must have a magnetic field. It must have a moon that stabilizes its climate and creates life-sustaining tides. It must have sufficient size and internal heat. It must avoid the extremes, not too hot like Venus, not too small like Mars. Each of these factors is necessary. Missing even one of them would render Earth uninhabitable. And yet, Earth possesses all of them. The probability of a single terrestrial planet possessing all of these characteristics is astronomically small. The probability of a single planetary system containing all of these characteristics, arranged in perfect harmony, is so small that it challenges even the largest probability calculations. And yet, here we are, living on Earth, breathing its air, drinking its water, sustained by its magnetic field and its stable climate. The question that now arises is not whether this is improbable. It is manifestly improbable. The question is, how did this improbability come to pass? How did Earth, by such an infinitesimal margin, end up being the one exception to the rule of cosmic barrenness? The answer we are beginning to uncover is that Earth's habitability is not an exception. It is not a fluke. It is the result of a system, and that system is the solar system. It is not Earth alone that is habitable. It is the solar system working together that creates habitability on Earth. And in understanding how the planets work together, we will come to understand something profound. We will come to understand that we do not live alone in the universe. We live in a partnership, A cosmic alliance that began 4.6 billion years ago and continues to this moment. An alliance between the Sun and 8 planets, between Jupiter's gravity and Earth's position, between the Moon's tidal pull and the oceans mixing, between the magnetic field generated by Earth's molten core and the solar wind that tries to strip our atmosphere away. We live in a system where nothing is truly separate. Everything influences everything else, and the habitability of Earth is the visible expression of that grand interconnection. In the next section, we will turn our attention to the Guardians, the planetary giants that stand between us and chaos. We will examine how they protect Earth from cosmic threats, how they organize the dynamics of the inner solar system, how they maintain the conditions that make complex life
possible. But first, let this moment of transition allow you to absorb what we have discovered so far. Let it settle into your awareness that you are not merely standing on a world. You are standing on a world maintained by an intricate balance of cosmic forces. Every breath you take is made possible by conditions created not only by Earth, but by the entire solar system working together. The air, the water, the stable seasons, the protection from radiation, all of it flows from a coordination so precise, so finely tuned, that it seems almost impossible. And yet it is real. It is happening. It has been happening for 4.6 billion years. And in understanding how it came to pass, we begin to glimpse the true miracle of life on Earth.
9. Jupiter S asteroid cleaner. Jupiter is a world so large that more than 1,300 Earths could fit inside its volume. It is the dominant planetary body in our solar system, aside from the Sun itself. It orbits at a distance of 778 million kilometers from the Sun, in a region called the Inner Solar System Boundary, where the inner rocky planets give way to the realm of gas giants. And Jupiter plays a role so profound in maintaining Earth's habitability that without it, complex life on Earth would likely never have evolved. The role Jupiter plays begins with asteroids. Between the orbits of Mars and Jupiter lies a region called the Asteroid Belt, a collection of millions of rocky bodies ranging in size from dust particles to objects hundreds of kilometers across. These asteroids are the remnants of planetary formation, material that never coalesced into a single planet because of gravitational perturbations caused by Jupiter's immense mass. The asteroid belt is a graveyard of failed planetesimals, frozen in time in their orbits around the Sun. Most of these asteroids remain safely in their orbits, neither approaching the inner solar system nor departing into interstellar space. But some do move. Gravitational interactions between asteroids, or subtle shifts in their orbital parameters caused by the gravity of the planets, occasionally nudge an asteroid from its stable orbit. When this happens, the asteroid's trajectory begins to change. Some asteroids are ejected outward, escaping into the outer solar system or beyond. Others are perturbed inward, their orbits bringing them closer to the Sun and, critically, closer to the inner planets, closer to Earth. If these asteroids reached Earth unimpeded, they would strike the planet as meteorites. Large ones would create impact craters. Very large ones would cause global catastrophes. In Earth's early history, such impacts were common. Evidence from lunar rocks and terrestrial geology shows that during the first 500 million years of the solar system's history, Earth experienced a period called the Late Heavy Bombardment, when asteroids and comets struck the planet with tremendous frequency. The surface was repeatedly scarred by impacts. The climate was destabilized. Oceans evaporated and reformed. Life, if it existed at all, struggled to gain a foothold. But here is where Jupiter enters the picture. Jupiter's gravity acts as a cosmic vacuum cleaner. When an asteroid's trajectory brings it into the inner solar system, Jupiter's immense gravitational field exerts an influence.
Some asteroids are captured into Jupiter's orbit, becoming moonlets or dissipating in collisions with Jupiter's existing moons. Others are deflected by Jupiter's gravity, their trajectories bent so severely that they are ejected from the solar system entirely. Others still are slowed enough by Jupiter's gravity that they fall into more stable orbits, remaining in the asteroid belt or settling into other safe regions. The net effect is
that Jupiter significantly reduces the number of asteroids that strike the inner planets, particularly Earth. Scientists estimate that without Jupiter's gravitational influence, the number of impact events on Earth would be roughly 100 to 1,000 times higher than what we observe today. The statistical difference is staggering. With Jupiter, impacts of very large asteroids strike Earth roughly once every 100 million years. Without Jupiter, such impacts might occur every 100,000 to 1 million years. A difference of this magnitude would transform Earth from a world where life thrives to a world where life is repeatedly driven to extinction. With such frequent impacts, complex organisms would never have time to evolve. Evolution requires stability. It requires long periods of time during which species can adapt to their environments, develop new characteristics, and establish themselves in ecological niches. Frequent extinction events would reset the evolutionary clock repeatedly, preventing the emergence of complex life forms. Consider the consequences of a large asteroid impact. When an object several kilometers in diameter strikes Earth at speeds of tens of kilometers per second, the energy released is equivalent to billions of nuclear weapons detonating simultaneously. The impact vaporizes rock at the point of impact, creating an enormous crater. Dust and ash are ejected into the stratosphere, blocking sunlight. Temperatures plummet. Photosynthesis ceases because plants cannot access sunlight. The food chain collapses. Organisms across the planet starve. Most life on Earth is extinguished in a geological instant. This is what happened 66 million years ago, when an asteroid roughly 10 kilometers in diameter struck what is now the Yucatan Peninsula in Mexico. The resulting extinction event, called the Cretaceous-Paleogene extinction, killed approximately 75% of all species on Earth, including the non-avian dinosaurs that had dominated the planet for 150 million years. If impacts of this magnitude occurred every million years instead of every 100 million years, the biosphere would never recover between extinctions. Life would be reduced to simple, hardy microorganisms capable of surviving in extreme conditions. Complex life would be impossible. Evolution would be stalled. Humanity would never exist. The protection that Jupiter provides is therefore not a minor detail in Earth's habitability. It is fundamental. It is the difference between a living biosphere and a barren world, repeatedly sterilized by cosmic violence. When you consider the emergence of life on Earth, the billions of species that have evolved, the intricate ecosystems that cover the planet, all of this is made possible by Jupiter's presence. Jupiter is not a distant, irrelevant body in the outer reaches of the solar system. It is an essential player in the drama of life on Earth. Every ecosystem, every species, every human civilization exists because Jupiter's gravity has been quietly removing asteroids from trajectories that would lead them to strike Earth. For 4.6 billion years, Jupiter has been performing this role. And this role has allowed life to flourish in a way that would otherwise be impossible. 10. The late heavy bombardment and the paradox of early life. 4 billion years ago, the early solar system was a very different place than it is today. The planets had formed, but they had not yet settled into their current stable orbits. The gravitational interactions between the giant planets, Jupiter, Saturn, Uranus, and Neptune, were more complex and chaotic than they are now. The asteroid belt and the region of icy bodies beyond Neptune were more densely populated, and the inner solar system, where Earth and the other terrestrial planets orbited, was under constant bombardment from asteroids and comets.
This period is called the Late Heavy Bombardment, and it lasted from approximately 4.1 billion years ago to 3.8 billion years ago, a span of roughly 300 million years. During this time, the impact rate on Earth was hundreds or thousands of times higher than it is today. The sky above Earth's surface would have been filled with streaks of light as asteroids and comets entered the atmosphere. The ground would have shaken from impacts. Enormous craters would have been excavated and then filled in by subsequent impacts. The climate would have been in constant chaos. Yet here is the paradox that has puzzled planetary scientists for decades. Evidence suggests that life on Earth originated during or shortly after this period of intense bombardment. Fossil evidence from rocks approximately 3.8 to 3.7 billion years old shows signs of organic molecules that may have been created by living organisms. Chemical isotope ratios in ancient rocks suggest that photosynthetic organisms may have existed 2.9 billion years ago. If life originated during a period of intense bombardment, how did it survive? How did it gain a foothold? How did it avoid being repeatedly extinguished by impacts that released energy equivalent to billions of megatons of TNT? The answer may lie in the nature of early life and the protection that deep oceans and underground environments could provide. If the earliest organisms were simple, single-celled microbes capable of surviving extreme conditions, they might have been able to shelter in hot springs, in the depths of the ocean, or in underground aquifers where impacts could not reach them. These environments would have been buffered from the worst effects of impact catastrophes. After each impact, surviving microbes could gradually repopulate the biosphere. Over hundreds of millions of years, life would gain stronger and stronger footholds, becoming more diverse and more resistant to extinction. But the late heavy bombardment did not last forever. Approximately 3.8 billion years ago, the bombardment gradually diminished. The impact rate decreased. The dynamics of the giant planets stabilized as they settled into more regular, predictable orbits. The asteroid belt became less densely populated as impacts cleared away much of its mass. The inner solar system became safer, more hospitable to life. And in the changing aftermath of the bombardment, complex life began to emerge. Simple, single-celled organisms evolved. Photosynthesis developed. Oxygen began to accumulate in the atmosphere. By 2.4 billion years ago, the atmosphere had become oxygen-rich, and multicellular organisms were beginning to evolve. The transition from the chaotic bombardment to the stable, life-filled world of the Proterozoic eon was profound. What caused the late heavy bombardment to end? The answer is believed to lie in the orbital migration of the giant planets. According to the Nice model, named after the city of Nice, France, where the theory was developed, the giant planets did not form in their current positions. Jupiter, Saturn, Uranus, and Neptune formed closer to the Sun in a more compact region. But over time, gravitational interactions between the planets and with the remaining planetesimals caused them to migrate. Jupiter migrated inward first, then outward. Saturn followed. Uranus and Neptune migrated outward as well. This migration happened over millions of years, but the gravitational effects were profound. As the giant planets migrated, they stirred the asteroid belt and the region beyond. Countless planetesimals were ejected from their stable orbits and sent careening inward or outward. This is the cause of the late heavy bombardment. The bombardment was not a continuation of the original planetary formation process. It was a consequence of the giant planets reorganizing their orbits. Eventually, the giant planets settled into their current orbital configuration. Jupiter and Saturn reached a stable relationship with each other. Uranus and Neptune completed their outward migration. The planetesimals that had been stirred were either ejected from the solar system, captured by the planets, or fell into impact craters on the terrestrial planets. The bombardment subsided. Stability returned. And in this stable aftermath, life flourished.
This means that the late heavy bombardment and its cessation were themselves consequences of the presence and orbital dynamics of the giant planets. Without Jupiter, Saturn, Uranus, and Neptune, the inner solar system would not have experienced this period of intense bombardment, but it also would not have been organized into its current, stable configuration. The current positions of Earth and the other terrestrial planets, positions that allow them to maintain stable orbits and habitable conditions, are the direct result of the giant planet's migration and eventual settlement. Earth's current habitability is therefore, in a profound sense, a consequence of having survived and adapted to the chaotic bombardment. Life on Earth emerged in the midst of cosmic violence. It learned to survive despite repeated catastrophes. And when peace finally came, when the bombardment ended and stability returned, life was already present, already thriving in its simple, resilient forms. Life did not need to emerge after the bombardment ended. It emerged during the bombardment itself. And this fact speaks to something deep about the nature of life and the universe. 11. Gravitational resonances and orbital stability. Imagine a group of musicians playing together. If each musician plays at a different tempo, the music becomes chaotic and unpleasant. But if the musicians synchronize their tempos, if they maintain a regular pattern of beats that relates to each other in simple ratios, the music becomes harmonious. Two musicians might alternate playing in a pattern of 2-to-1. One plays 2 notes for every 1 note the other plays. Or they might maintain a 3-to-2 pattern, 3 notes for every 2. Whatever the pattern, as long as it is consistent and based on simple integer ratios, harmony emerges. The orbits of planets around the Sun follow a similar principle. When 2 planets orbit the Sun with orbital periods that maintain a simple integer ratio, their orbits are said to be in resonance. These resonances create patterns of gravitational interaction that can either stabilize the orbits or destabilize them, depending on the specific configuration. Orbital resonances are fundamental to understanding why the planets in our solar system orbit where they do, and why their orbits remain relatively stable over billions of years. Earth and Venus provide an example of a near resonance that stabilizes their orbits relative to each other. Venus orbits the Sun in approximately 225 Earth days. Earth orbits in 365 Earth days. The ratio is approximately 0.616 to 1, which is not a simple integer ratio, but it is close enough to create gravitational effects that prevent Venus and Earth from approaching each other too closely. The resonance is not perfect, but it is close enough to be dynamically significant. The result is that Venus and Earth maintain stable, non-intersecting orbits. They never approach each other closely. Their mutual gravitational attraction remains small and manageable. This stability has persisted for 4.6 billion years, and it will persist for billions of years more, as long as the solar system remains intact. More dramatically, Jupiter and Saturn maintain an important resonance. Jupiter orbits the Sun with a period of approximately 12 Earth years. Saturn orbits with a period of approximately 29.5 Earth years. The ratio of their orbital periods is approximately 2.5 to 1, which is not exactly a simple integer ratio, but it is close to 5 to 2. This near resonance creates a complex pattern of gravitational interactions between the 2 giant planets. The resonance prevents Jupiter and Saturn from migrating inward towards the Sun. It stabilizes their orbits. It also has the effect of organizing the dynamics of the entire inner solar system. The gravitational effects of Jupiter and Saturn, mediated by their resonance, create a pattern of stable and unstable orbital zones in the region where Earth, Venus, Mars, and Mercury orbit. Earth's orbit falls within a stable zone. Other potential orbital zones are unstable, and any planets that might have formed in those zones would have been ejected into the inner or outer solar system or collided with other bodies. Earth occupies a stable zone because of the resonance between Jupiter and Saturn. Resonances are not always stabilizing. Sometimes they create chaos.
There is a region in the asteroid belt called the Kirkwood Gaps, regions where very few asteroids orbit. These gaps exist because asteroids in those regions would maintain resonances with Jupiter's orbital period. These resonances would cause the asteroids' orbits to become increasingly elongated over time, eventually becoming so elongated that they intersect Jupiter's orbit. Asteroids on such orbits would inevitably collide with Jupiter, be ejected from the solar system, or scatter into other regions. Over billions of years, all the asteroids that would have naturally occupied the Kirkwood Gaps have been removed. Only asteroids in non-resonant orbits persist in the asteroid belt. The existence of the Kirkwood Gaps proves that resonances profoundly influence the structure of the planetary system. If Earth's orbit were in a destabilizing resonance with Jupiter, Earth's orbit would gradually become more elongated. Over millions of years, Earth might swing closer to Venus at perihelion, its closest approach to the Sun, and farther from the Sun at aphelion, its farthest distance. Large orbital variations like this would destabilize Earth's climate. Seasonal temperature variations would become extreme. Some regions would experience baking heat, others freezing cold. Life would be driven to extinction. But Earth's orbit is not in a destabilizing resonance with Jupiter. It maintains a position of orbital stability. The gravitational effects of Jupiter, mediated through resonances with Saturn and other planets, maintain Earth's orbit in a stable, nearly circular path around the Sun. This stability has persisted for billions of years, and this stability is absolutely essential for Earth's habitability. When you contemplate the motion of the planets, you are contemplating something that appears random and chaotic at first glance. But upon closer examination, you discover deep mathematical patterns. Resonances, harmonies, gravitational relationships that organize the entire system. Earth's orbit is not a chance occurrence. It is not a random configuration that might equally well be replaced by any other orbital arrangement. It is one of the very few stable orbits possible, given the gravitational presence of the other planets. And it is precisely in this stable orbit that Earth remains, generation after generation, century after century, billion year after billion year. Maintaining conditions suitable for life, through the simple fact that its motion is coordinated through gravity with the motion of Jupiter and Saturn, and all the other celestial bodies that make up our solar system.
12. The chaos threshold. If Jupiter were 10% closer, computer scientists and mathematicians have developed tools to simulate the dynamics of planetary systems. These simulations can track the orbits of planets over millions or billions of years, accounting for gravitational interactions between all the bodies in the system. They can be used to answer hypothetical questions. What would happen if a planet were in a different orbit? What if a planet were more massive? What if a planet were missing entirely from the system? When planetary scientists ask these questions about Jupiter, the answers are both revealing and disturbing. Simulations show that if Jupiter were positioned just 10% closer to the Sun than it currently is, if it orbited at 700 million kilometers instead of 778 million kilometers, the dynamics of the inner solar system would change catastrophically. With Jupiter 10% closer to the Sun, the resonances between Jupiter and Saturn would be different. The pattern of gravitational interactions that currently stabilizes Earth's orbit would be disrupted. The inner solar system would become chaotic. Mercury, Venus, Earth, and Mars would begin to experience gravitational perturbations that gradually altered their orbits. Some of these perturbations would be small at first, causing slight variations in orbital eccentricity or inclination. But over millions of years, these small perturbations would accumulate. The variations would become larger. Eventually, one or more of the terrestrial planets would be perturbed so severely that their orbit would become unstable.
They might collide with each other. They might be ejected from the solar system entirely. They might spiral into the sun. The detailed outcome depends on the specific simulation and the specific initial conditions, but the general pattern is consistent across hundreds of different simulations. The inner solar system becomes unstable. The planets do not remain in their current orbits. Catastrophe follows. In some simulations, if Jupiter were 10% closer to the Sun, Mars and Earth would eventually enter into a collision course with each other. In others, Venus would be perturbed into an orbit that intersects Earth's path, leading to collision. In still others, one or more planets would be ejected from the solar system entirely, becoming rogue planets wandering through interstellar space. Some simulations show Mercury being scattered outward, colliding with Venus. Others show multiple planets colliding in a cascade of gravitational chaos. But in virtually all of the simulations, one outcome is consistent. Earth's current orbit is not maintained. Earth is not left in a stable, habitable configuration. The planet either collides with another body or is ejected from the solar system. Either way, life on Earth would be destroyed. The timeline for this catastrophe might be millions of years or billions of years, depending on the specifics, but the end result inevitable.
What makes this thought experiment so profound is the realization of how fragile Earth's habitability truly is. The solar system is not an inevitable, stable configuration that could exist in essentially any form and still support life. The current configuration of the planets, the specific distances at which they orbit, the specific masses they possess, is one of the very few configurations that allows for stable, long-lived planetary orbits in the habitable zone. Changing Jupiter's position by just 10% destroys stability. Moving it 15% closer would likely produce even more rapid chaos. But our Jupiter is exactly where it needs to be. It orbits at 778 million kilometers, a distance that maintains the resonances and gravitational relationships necessary for the inner planets to remain in stable orbits. Earth is therefore not habitable by accident. It is habitable because it occupies an orbit that is stable, and that orbit is stable because of Jupiter's presence and position. The probability of a planetary system forming with a large planet like Jupiter at exactly the right distance to stabilize the inner planets is not zero, but it is very small. Astronomers have discovered thousands of exoplanetary systems around other stars. In most of these systems, Jupiter-like planets are either absent entirely or are positioned much closer to their star than Jupiter is to our Sun. Systems with a large outer planet at approximately the right distance to stabilize a habitable zone terrestrial planet are relatively rare. And even in systems with an appropriately positioned outer planet, the terrestrial planets may not be in habitable zones, or their atmospheres may not be suitable for life, or they may lack a large moon to stabilize their climate, or any number of other conditions might be wrong. The combination of all factors necessary for habitability is extraordinarily rare. But Earth has all of them. Earth's position, with Jupiter at the right distance to stabilize its orbit, is not merely habitable, it is uniquely suited to allow complex life to flourish over geological timescales. When you consider this fragility, when you realize that Earth's habitability depends on Jupiter being positioned not approximately at the right distance, but precisely at the right distance, within a tolerance of perhaps just a few percent, you begin to comprehend the depth of Earth's improbability. You are not standing on a world that is naturally habitable. You are standing on a world that is habitability itself, only made possible by a specific arrangement of celestial bodies that maintains perfect gravitational harmony across billions of years. 13. The 12-year dance. Jupiter's orbital cycle. Time moves differently in the cosmos than it does on Earth. When you measure your life in years and decades, you are measuring by the rotation of Earth around the Sun. But Jupiter measures time by its own rhythm. Jupiter takes approximately 12 Earth years to complete a single orbit around the Sun. This means that while you have lived 1 decade of your life, Jupiter has barely completed one complete journey around its star. For Jupiter, a year is an eternity compared to an Earth year. But for the solar system, Jupiter's 12-year cycle is a fundamental rhythm, a cosmic heartbeat that resonates through the entire system and influences patterns on Earth in ways that science is only beginning to fully understand. The 12-year cycle of Jupiter has been known since ancient times. Babylonian astronomers observed Jupiter's movement across the sky and noted that it completed a full circuit roughly every 12 years. They used this observation for astrological purposes, dividing the zodiac into 12 houses corresponding to Jupiter's position at different times of the year. Medieval European astronomers continued to observe Jupiter's cycle and incorporated it into their models of the heavens. But the significance of this cycle goes far deeper than ancient astrology could perceive. The 12-year cycle is more than just a measure of Jupiter's motion. It is a pattern that influences the gravitational architecture of the entire inner solar system. As Jupiter orbits the Sun, its position relative to the other planets changes continuously. The angle between Jupiter and Earth shifts through a complete 360-degree rotation approximately every 13 months, a period astronomers call the synodic period of Jupiter. During this time, Earth and Jupiter return to the same relative positions they occupied 13 months earlier. This cyclical alignment creates patterns of gravitational interaction between Earth and Jupiter that repeat on this 13-month cycle. But Jupiter's interaction with Saturn, with Mars, and with the asteroid belt creates longer period patterns that take 12 years to complete. Scientists have discovered that these 12-year cycles correlate with variations in solar activity, with changes in Earth's weather patterns, and possibly with fluctuations in the number of sunspots observed on the solar surface. Some researchers have proposed that Jupiter's 12-year cycle influences the Earth's climate through complex mechanisms involving solar activity. When Jupiter reaches certain positions in its orbit, its gravitational effects on the Sun's corona may subtly influence the Sun's output of energy. This would create an 11 to 12-year cycle in solar output, which would then cause variations in Earth's climate. Other scientists suggest that Jupiter's gravitational influence affects the trajectories of cosmic ray particles, which in turn influence cloud formation in Earth's atmosphere, which affects climate. The mechanisms are complex
and still not fully understood. But the correlation between Jupiter's cycle and Earth's weather patterns is striking enough that it cannot be dismissed as coincidence. Beyond climate, Jupiter's 12-year cycle also influences patterns in Earth's magnetosphere and in the behavior of Earth's magnetic field. The Norwegian scientist Arnor Kruger proposed in the 1970s that variations in solar activity follow an 11-year cycle related to Jupiter's orbital dynamics. This cycle is now called the Schwabe cycle, named after an earlier German astronomer who observed it. The cycle represents variations in the number of sunspots, in the intensity of solar flares, and in the amount of radiation emitted by the Sun. All of these vary in an approximately 11-year pattern that closely tracks Jupiter's position. If this relationship is real, as many solar physicists now believe it is, then Jupiter's motion around the Sun exerts an influence on solar activity, which exerts an influence on Earth's upper atmosphere, magnetosphere, and ultimately on life on the surface. The mechanism by which Jupiter influences solar activity is still debated among scientists. One proposed mechanism involves Jupiter's gravity affecting the motion of charged particles in the Sun's magnetosphere, subtly altering the structure of the Sun's magnetic field, and therefore the rate of energy release through solar flares. Another proposes that Jupiter's orbit affects the barycenter, the center of mass of the solar system. As Jupiter moves, it carries a tremendous amount of mass with it, and the center of mass of the entire solar system shifts in response. The Sun orbits around this barycenter, not around a fixed point in space. The Sun's motion relative to the solar system's center of mass may influence internal solar processes that regulate energy output. None of these mechanisms is proven beyond doubt, but the correlations are strong enough that most solar scientists now accept that Jupiter's motion influences solar activity to some degree. This means that Jupiter's 12-year cycle is more than an abstract astronomical pattern. It is a rhythm that connects Jupiter's motion to the Sun's behavior, to Earth's climate, to the storms in Earth's atmosphere, to the lives of organisms on the surface. Every 12 years, as Jupiter completes another orbit around the Sun, the entire solar system passes through a complete cycle of gravitational configurations, and each cycle leaves its mark on Earth, in weather patterns and atmospheric processes, and in the lives of creatures that depend on stable climate. You are not merely living on a static Earth. You are living on a world caught in the rhythms of a vast celestial dance, where Jupiter's motion 12 years ago influences whether today will be stormy or clear, cold or warm. The cycles repeat, the patterns persist, and Jupiter, dancing its ancient dance around the Sun, continues to conduct an invisible orchestra of gravitational influences that cascade down to affect
Life on the surface of Earth.
14. Saturn and the second shield. Beyond Jupiter, in a region even farther from the Sun, orbits Saturn. Where Jupiter is massive and fierce, a gas giant of terrible gravity, Saturn appears almost gentle by comparison. Saturn is nearly as large as Jupiter, containing approximately 95 times the mass of Earth. But it is less dense. If you could place Saturn in a hypothetical cosmic ocean, it would float. Saturn orbits at approximately 1.4 billion kilometers from the Sun, nearly twice as far as Jupiter. Saturn takes approximately 29.5 Earth years to complete a single orbit, meaning that a person born on Earth would need to live more than 29 years before Saturn returned to the same position in its orbit that it occupied at their birth. Saturn seems like a distant observer, a remote planetary body with little influence on the inner solar system. But this appearance is deceptive. Saturn plays a crucial complementary role to Jupiter in protecting the inner solar system and maintaining the stability of Earth's orbit. While Jupiter is the primary gravitational perturber of asteroids and comets, redirecting many of them away from the inner planets, Saturn's role is more subtle, but equally important. Saturn and Jupiter are locked together in a gravitational resonance, a coordinated dance that has persisted for billions of years. Jupiter completes approximately 2.5 orbits for every one orbit that Saturn completes. This 5-to-2 resonance creates a pattern of gravitational interaction between the two gas giants. The resonance acts like a barrier, a demarcation line in the solar system that separates the inner region from the outer region. This barrier helps prevent asteroids and comets from the outer regions from drifting too far inward toward the inner planets. The specific nature of Jupiter-Saturn resonance is that it creates what astronomers call a secular resonance, a long-period oscillation in the orbital parameters of other bodies that interact gravitationally with both Jupiter and Saturn. This resonance influences the orbits of Mars and the asteroids in the asteroid belt. It creates regions that are dynamically stable and regions that are unstable. Earth's orbit falls in a region that benefits from this resonance structure. The combined gravitational effects of Jupiter and Saturn, mediated through their 5-to-2 resonance,
organize the dynamics of the asteroid belt in such a way that asteroids are preferentially ejected from the solar system or held in stable orbits, rather than being sent careening toward the inner planets on collision courses. Saturn also performs a role in relation to comets. The region beyond Neptune contains billions of icy bodies collectively known as the Oort cloud. Occasionally, gravitational perturbations from passing stars or from chaotic interactions among the icy bodies cause one or more comets to leave the Oort cloud and plunge into the inner solar system. These comets are the source of the long-period comets that occasionally become visible from Earth. Without the gravitational influence of the outer planets, many more of these comets would reach the inner solar system. But Saturn and Jupiter and Uranus and Neptune intercept many of these comets, deflecting them or capturing them into stable orbits. Saturn in particular, with its large mass and its position between Jupiter and the outer planets, plays an important role in this protective function. The most famous event related to this protective function occurred in July of 1994, when the comet Shoemaker-Levy 9, which had been captured into orbit around Jupiter, collided with Jupiter's atmosphere. The comet had been torn apart by gravitational stress into approximately 20 separate fragments, each ranging from a few hundred meters to a few kilometers across. Over a period of 6 days, these fragments struck Jupiter's atmosphere one after another. Each impact released enormous energy, creating fireballs and scars in Jupiter's clouds that were visible from Earth through telescopes for weeks. The collision was observed by astronomers around the world, and many realized the profound implications. If Jupiter had not been present in the solar system, if the comet had not been captured by Jupiter's gravity, it might have reached the inner solar system. It might have struck Earth. An impact by fragments of this size would have been catastrophic, potentially triggering a mass extinction event similar to the one that killed the dinosaurs. Saturn cannot perform this protective function alone. It is too far from the inner solar system to directly intercept most comets heading inward. But Saturn maintains the resonance with Jupiter that organizes the dynamics of the entire system. Saturn enforces the structure that Jupiter uses to protect the inner planets. Together, Jupiter and Saturn form a complementary system, one more massive and closer, providing direct protection. The other more distant, providing structural reinforcement. Remove Saturn, and the resonance that keeps the inner solar system organized would be disrupted. The chaos that follows might destabilize Earth's orbit. Similarly, remove Jupiter, and Saturn would have no resonance partner, and the outer solar system would become chaotic. The two gas giants are not independent actors. They are partners in a vast, coordinated effort to maintain habitability on Earth. When you look at Saturn in the night sky and see its rings glowing faintly in the darkness, you are looking at a guardian that works in partnership with Jupiter. You are looking at a body that, though 1.4 billion kilometers distant, exerts a gravitational influence that keeps Earth safe. The rings of Saturn, those beautiful bands of ice and rock, are themselves evidence of Saturn's power. The remnants of moons torn apart by gravitational stress, or material that was prevented from coalescing into a moon by subtle gravitational perturbations. Saturn is a sculptural force in the solar system, and its sculpture
Includes the maintenance of the conditions necessary for life on Earth. 15. Uranus and Neptune, the distant guardians. Beyond Saturn lie two planets that most people rarely think about, Uranus and Neptune. These are called the ice giants, in distinction from Jupiter and Saturn, which are called gas giants. Uranus orbits at approximately 2.9 billion kilometers from the Sun, taking 84 Earth years to complete a single orbit.
Neptune orbits even farther, at approximately 4.5 billion kilometers, taking 165 Earth years per orbit. From Earth, both planets are invisible to the naked eye. Even through small telescopes, they appear as featureless disks with no detail visible. Yet these distant, overlooked worlds play a critical role in maintaining the habitability of the entire inner solar system. The primary role of Uranus and Neptune is to maintain the structure of the Oort cloud, the vast, diffuse, spherical shell of icy bodies that surrounds the entire solar system. The Oort cloud contains billions, or possibly trillions, of icy bodies, the remnants of planetary formation from the outer regions of the nebula that gave birth to the solar system. These bodies orbit at distances ranging from perhaps 2,000 astronomical units from the Sun to perhaps 100,000 astronomical units or more. They are so distant that the Sun appears to them as merely another star in the sky, not a significant gravitational center. Yet, these bodies are still bound to the solar system by the gravity of the giant planets, especially Uranus and Neptune. The gravity of Uranus and Neptune maintains the Oort cloud in a relatively stable configuration. Without their gravitational influence, the icy bodies in the Oort cloud would gradually escape into interstellar space, or be perturbed into highly eccentric orbits that would send them careening into the inner solar system. Over billions of years, the Oort cloud would dissipate. The steady population of long-period comets that occasionally venture into the inner solar system would come to an end. But more importantly, without Uranus and Neptune maintaining the structure of the Oort cloud, the comets that are occasionally perturbed inward would be far more numerous and more violent. The bombardment rate on Earth would increase dramatically. Complex life would be driven to extinction repeatedly. When astronomers calculate the trajectories of long-period comets, they often find that these comets originated in the Oort cloud. A close encounter between two icy bodies in the cloud, or the gravitational perturbation from a passing star, nudged the comet from its stable orbit. It fell inward, pulled by the gravity of the inner solar system. As it approached the inner planets, it was sometimes further deflected by Jupiter or Saturn, preventing collision with Earth. Sometimes, it was captured into a highly elliptical orbit and became a periodic comet, a body that returns to the inner solar system at regular intervals. The comet Halley, famous for returning every 76 years, is an example of such a captured periodic comet.
Its original orbit was in the Oort cloud, but now it is locked into a repeating pattern that brings it close to Earth on a regular schedule. Uranus and Neptune perform another protective function as well. Beyond Neptune's orbit, in a region called the scattered disk, there is another population of icy bodies that are not as distant as the Oort cloud, but are still quite far from the Sun. These scattered disk objects occasionally have their orbits perturbed inward by gravitational interactions with Neptune. When this happens, they plunge toward the inner solar system. But Neptune's gravity often deflects them before they reach dangerously close to Earth. Jupiter and Saturn provide additional protection. A careful choreography of gravitational interactions, with Uranus and Neptune acting as the outermost guards, prevents most of these bodies from reaching Earth. Those that do are typically small enough that they burn up in Earth's atmosphere as meteors, rather than striking the surface as large impacts. The role of Uranus and Neptune becomes even more clear when you consider the dynamics of the early solar system. During the late heavy bombardment, approximately 3.8 to 4.1 billion years ago, the gravitational interactions between Jupiter, Saturn, Uranus and Neptune created the very bombardment that would have sterilized Earth multiple times. Yet these same planets, by organizing and eventually settling into their current orbital configuration, brought the bombardment to an end. They transformed the solar system from a chaotic maelstrom of collisions to a relatively stable system where complex life could flourish. And they have maintained this stability ever since, by continuing to protect the inner solar system from excessive bombardment. Uranus is unusual among the planets in that its axis of rotation is tilted at approximately 98 degrees,
It essentially orbits the Sun on its side. Neptune's axis is tilted at approximately 30 degrees. This unusual tilt on Uranus and the relatively large tilt on Neptune are believed to be consequences of gravitational interactions with other planetesimals during the chaotic early solar system. These tilts may seem irrelevant to Earth's habitability, but they are not. The tilts influence the orbital dynamics of these planets. They influence the structure of the Oort cloud. They influence the precise pattern of gravitational effects that these distant planets exert on the rest of the solar system. If Uranus or Neptune had different tilts, if they had different masses, if they were in different orbits, the protective effects they provide would be altered. Earth might be less well protected. The bombardment rate might be higher. Life might be less likely to flourish. When you consider the vast distances involved, Uranus orbiting 20 times farther from the Sun than Earth, Neptune orbiting 30 times farther, it seems almost impossible that their actions could matter to life on Earth. Yet they do matter. Profoundly.
The gravity of these distant worlds reaches across billions of kilometers of space to influence the trajectories of comets, to maintain the structure of the Oort cloud, to protect Earth from cosmic hazards. These planets are not merely ornaments on the periphery of the solar system. They are essential guardians, maintaining the conditions necessary for Earth's habitability from their distant vigil at the edge of the solar system. 16. The Kuiper belt and the boundary of protection. Between Neptune's orbit and the far more distant Oort cloud lies a region called the Kuiper belt. This region, extending from approximately 30 astronomical units to approximately 55 astronomical units from the Sun, is populated by thousands of icy bodies, ranging in size from a few kilometers to more than 2,000 kilometers across. Pluto, which was reclassified from a planet to a dwarf planet in 2006, is one of the largest objects in the Kuiper belt. Other notable residents include Eris, Haumea, and Makemake. The Kuiper belt is not a dense swarm like the asteroid belt. Objects are separated by vast distances. A spacecraft traveling at the speed of the fastest human-made vehicles would take years to travel from one Kuiper belt object to another. Yet the Kuiper belt is populated densely enough that it represents a significant population of solar system bodies. And it represents a critical boundary between the relatively well-organized inner solar system and the vast, diffuse Oort cloud beyond. The Kuiper belt marks a transition zone. Inside the Kuiper belt, the solar system is relatively well-organized. Planetary orbits are stable. The asteroid belt is under control. Earth orbits safely in its habitable zone. Outside the Kuiper belt, in the Oort cloud, things are far more chaotic. Billions of icy bodies orbit in a semi-random distribution, their orbits influenced primarily by gravity rather than by the organized patterns of resonance that characterize the inner solar system. The Kuiper belt represents the boundary between these two regimes. It is the last organized structure in the solar system. Beyond it lies chaos. The Kuiper belt itself is partially the product of planetary migration. When Jupiter, Saturn, Uranus, and Neptune were forming, they accumulated material from a much larger region than they currently occupy. According to the Nice model, the giant planets migrated outward over time, scattering material as they went. The Kuiper belt represents material that was left behind or captured as the giant planets migrated. When Uranus and Neptune migrated outward, they scattered icy bodies. Many of these bodies were ejected from the solar system entirely. Others fell inward toward the Sun. Still others settled into stable orbits in the Kuiper belt region. The result is that the Kuiper belt today is partially a product of the gravitational sculpture performed by the giant planets billions of years ago.
Objects in the Kuiper belt can be perturbed into different orbits by gravitational interactions with Neptune or by close encounters with other Kuiper belt objects. When this happens, some objects are ejected outward into the Oort cloud, where they join the vast population of long-period comets. Others are scattered inward, sent on trajectories that carry them toward the inner solar system. These scattered objects become long-period comets that enter the inner solar system occasionally, returning to their Oort cloud homes after each passage. The rate at which Kuiper belt objects are scattered inward and become visible as comets is related to the density of the Kuiper belt and to the specific orbital configuration of Neptune. Throughout most of solar system history, the Kuiper belt has maintained a relatively stable population. Objects are scattered slowly, gradually populating the Oort cloud and occasionally sending comets into the inner solar system. But there are periods when the Kuiper belt becomes more active. During these periods, more objects are scattered inward. The rate of cometary impacts on Earth increases. These periods may correlate with variations in Earth's climate, with increases in extinction rates, or with other disturbances to the biosphere. If the Kuiper belt were more densely populated, the rate of cometary impacts would be higher. If it were less densely populated, impacts would be rarer. Earth's habitability is therefore influenced by the density of the Kuiper belt, which in turn is influenced by the gravitational configuration of the outer planets. The Kuiper belt also represents a store of water and organic compounds. The icy bodies in the Kuiper belt contain frozen water, carbon dioxide, methane, and other compounds essential for life. When a comet from the Kuiper belt falls into the inner solar system and is heated by the sun, some of these compounds vaporize and become visible as the comet's tail. Some scientists have proposed that much of Earth's water and organic compounds were delivered to Earth by comets during the late heavy bombardment. If this is true, then the Kuiper belt and the Oort cloud are not merely sources of danger through bombardment. They are also suppliers of the raw materials necessary for life. Without the Kuiper belt and its population of icy bodies, Earth might never have received the water and organic compounds necessary to support the chemistry of life. The Kuiper belt represents both a threat and a resource. It is a source of comets that occasionally collide with Earth, threatening life through impact. Yet it is also a source of the water and organic compounds that form the basis of life. This duality reflects a deeper truth about the solar system. Each component plays multiple roles. Nothing is purely protective or purely threatening. Everything influences everything else. The Kuiper belt's position, its density, its population of icy bodies, all of these are consequences of the gravitational organization of the solar system performed by the giant planets over billions of years. And all of these consequences have reverberated down to affect the habitability of Earth, a small, rocky world orbiting a modest star, 4.5 billion kilometers on the other side of the solar system. 17. The Grand Tack, Jupiter's journey through time. Imagine a planetary system in its infancy, barely 1 million years old. Dust and gas swirl in a disk around the young sun. Small bodies collide and merge, gradually coalescing into larger objects. The planets have not yet formed. The solar system has not yet taken on the structure we recognize today. Instead, there is only chaos, a dense nebula of material, a churning cauldron where planetary bodies are being born. This is the primordial solar system. And Jupiter is not where it is today. According to the most widely accepted theory of planetary formation and migration, Jupiter formed farther from the Sun than it currently orbits, and then it moved. The theory is called the Grand Tack,
and it proposes that Jupiter, early in its history, migrated inward toward the Sun. As Jupiter grew larger through accretion of material, its gravitational influence on the remaining planetesimals increased. Jupiter pulled material toward itself, consuming it and growing even more massive. As Jupiter accumulated more material, it became so massive that it was no longer pulled around by the gravity of other bodies. Instead, it began to pull on them. Jupiter's inward migration would have had catastrophic effects on the inner solar system. It would have stirred up asteroids and planetesimals in the inner regions. It would have caused collisions and disruptions. The orbits of Mercury, Venus, and Mars would have been destabilized. The young Earth might have been knocked out of its orbit, sent careening into the Sun or out into interstellar space. The solar system might have been destroyed before it barely begun. But then something unexpected happened. As Jupiter migrated inward, it approached Saturn. Saturn, which had also been forming and migrating, had grown into a planetary body of considerable mass itself. When Jupiter and Saturn approached each other, their mutual gravity began to interact. A complex gravitational dance began. According to the grand Tack theory, Jupiter migrated inward until it came very close to Saturn, perhaps as close as 1.5 astronomical units from the Sun, while Saturn remained farther out. At that point, the two planets entered a resonance. They became locked in a specific orbital relationship, a 3-to-2 resonance, meaning that for every 3 orbits Jupiter completed, Saturn completed 2. This resonance was stable, and it had a profound effect. The resonance created a gravitational barrier that prevented further inward migration. Jupiter could not penetrate deeper toward the Sun without losing its resonance with Saturn. Then, the migration reversed. Through mechanisms that are still not entirely understood, possibly through interactions with remaining planetesimals, or through subtle gravitational effects of the disk of gas and dust that surrounded the young Sun, Jupiter and Saturn began to migrate outward. As they moved, they continued to maintain their resonance, their 3-to-2 orbital dance.
Jupiter moved outward faster than Saturn, but they remained in locked step with each other. This outward migration would have stirred the asteroid belt and the Kuiper belt violently. Planetesimals would have been scattered. Some would have been ejected from the solar system. Others would have been flung inward toward the inner planets. This is believed to be the cause of the late heavy bombardment, the period of intense impacts that scarred Earth's surface 4.1 to 3.8 billion years ago. But even though the late heavy bombardment was destructive, it may have been necessary. The inward migration of Jupiter and the subsequent outward migration of Jupiter and Saturn reorganized the solar system into a stable configuration. When the migration was complete, the planets settled into roughly their current positions. Jupiter was at 5.2 astronomical units from the Sun. Saturn was at 9.5 astronomical units. The terrestrial planets, Mercury, Venus, Earth, and Mars, remained in the inner solar system, in stable, non-intersecting orbits. The asteroid belt had been partly cleared, but left with enough material to create the population we see today. The Kuiper belt had been populated by planetesimals, scattered outward by Jupiter and Saturn. The Oort cloud had been seeded with icy bodies from throughout the solar system. The significance of the grand Tack cannot be overstated. Without this migration, Earth might not exist, or if it did exist, it might not be in a habitable orbit. Without the inward and outward migration of Jupiter and Saturn, the terrestrial planets would still be in unstable, chaotic orbits. The solar system would be in a state of perpetual disruption. Complex life would not have had time to evolve. The grand Tack is therefore not merely an interesting detail of solar system history. It is the event that created the conditions necessary for Earth's habitability. It is the event that allowed life to eventually emerge and flourish. Every human civilization, every species, every individual organism on Earth exists because Jupiter and Saturn underwent this migration billions of years ago. But the Grand Tack is a recent theory. It was developed in the early 2000s by a team of planetary scientists, including Konstantin Batygin, Alessandro Morbidelli, and others. Before this theory, astronomers had been puzzled by the structure of the solar system. The positions of the planets seemed almost random. Jupiter and Saturn seemed to be in strange locations. Planets in other solar systems around other stars often orbited much closer to their stars than Jupiter does. Why was Jupiter so far from the Sun? Why did it stop migrating outward when it did? The Grand Tack theory provided answers. It explained why the solar system has the structure it does. And in explaining the structure of the solar system, it explained why Earth is habitable. The theory emerged from decades of research into planetary dynamics, computer simulations, and analysis of exoplanetary
Systems. It represents one of the greatest achievements in modern planetary science. 18. The Grand Tack Reverberations, Effects on the Terrestrial Planets. The inward and outward migration of Jupiter and Saturn did not merely reorganize the outer solar system. It had profound effects on the terrestrial planets, Mercury, Venus, Earth, and Mars. Each of these planets was influenced by the gravitational stirring caused by Jupiter's migration. Their orbits were perturbed. Some were knocked inward toward the Sun, others were pushed outward away from the Sun. Some were scattered entirely, their orbits becoming chaotic and unstable. In the end, the planets that we see today, Mercury, Venus, Earth, and Mars, are the survivors of this great cosmic upheaval. They are the planets whose orbits remained stable enough, after all the perturbations, to persist in relatively unchanged form to the present day. Mercury may have been knocked closer to the Sun than it originally formed. Computer simulations suggest that Mercury's current position, very close to the Sun in a highly eccentric orbit, may not be its original location. Early in solar system history, Mercury may have formed farther from the Sun, but was scattered inward by gravitational interactions with other planets during the Grand Tack. Venus may have undergone similar perturbations, though its current orbit is more nearly circular than Mercury's, suggesting that it settled into a more stable location after the migration events concluded. Mars appears to have been particularly affected by the Grand Tack. Some simulations suggest that Mars's relatively small mass, only about 11% of Earth's mass, is a consequence of the Grand Tack. If Jupiter migrated inward through the region where Mars was forming, Jupiter would have scattered planetesimals and prevented Mars from accreting as much material as it might have otherwise. Mars would have remained small and relatively isolated. Earth was affected as well, though perhaps less dramatically than Mars. Computer simulations of the Grand Tack show that Earth's orbit was perturbed by the inward and outward migration of Jupiter and Saturn. Earth may have been knocked slightly closer to or farther from the Sun. Its orbit may have become more or less eccentric for periods of time before eventually settling into its current, nearly circular path at 1 astronomical unit from the Sun. The fact that Earth's current orbit places it in the habitable zone, where liquid water can exist on the surface, may itself be partially a consequence of the Grand Tack. The migration of Jupiter and Saturn may have nudged Earth's orbit into exactly the right location. Without this gravitational nudge, Earth's orbit might be slightly different, perhaps close enough to put Earth outside the habitable zone, perhaps far enough to place it in a region that is too cold for liquid water. The evidence for the Grand Tack comes from multiple sources. Computational simulations of planetary dynamics can reproduce the structure of the solar system if one assumes that Jupiter and Saturn underwent the migration pattern predicted by the theory. The simulations show that starting from a primordial solar system with a different planetary configuration, the Grand Tack leads naturally to the solar system we see today. The simulations also show that without the Grand Tack, the solar system would have a very different structure, one in which planets would likely not be in stable orbits, and the prospects for life would be much worse. Additionally, observations of exoplanetary systems around other stars provide supporting evidence. Many of these systems show evidence of planetary migration. Some systems have hot Jupiters, gas giants orbiting very close to their stars, having migrated inward and not migrated back outward. These observations suggest that planetary migration is a common phenomenon, and that the Grand Tack is likely an example of this general pattern. The implications of the Grand Tack for Earth's habitability are profound. The current configuration of the solar system, with Earth at exactly the right distance from the Sun, in a stable orbit that allows for liquid water, is not inevitable. It is the product of a specific sequence of gravitational events that began with Jupiter's inward migration. If Jupiter had not migrated inward, the Grand Tack would not have occurred. Jupiter and Saturn would not have entered into their resonance. The subsequent outward migration would not have happened. The solar system would have a different structure. Earth might not exist, or if it did, it would likely not be in a habitable orbit. The chain of causation runs backward through time. Earth's current habitability flows backward through the Grand Tack to Jupiter's early inward and outward migration, and before that, to Jupiter's formation itself. When you consider the vast distances involved, Jupiter migrating millions of kilometers inward and then millions of kilometers outward, and the vast timescales involved, these migrations occurring over millions of years in the early solar system, it seems almost inconceivable that such processes could influence life on Earth. Yet they did. The Grand Tack, occurring 4.6 billion years ago, in the first few million years of solar system history, determined the structure of the solar system, which determined the habitable zone, which allowed Earth to be in a habitable location, which allowed life to emerge. The Grand Tack is therefore not merely a curious event in solar system history. It is the foundational event upon which all of Earth's habitability rests.
19. Why other solar systems lack protective Jupiters. Since 1995, when the first exoplanet was discovered orbiting the star 51 Pegasi, astronomers have discovered more than 5,500 exoplanets orbiting around stars other than the Sun. These discoveries have revealed that planetary systems are far more diverse than anyone anticipated. Some systems have multiple gas giants, some have only rocky planets, some have planets in very close orbits around their stars, some have planets in very distant, wide orbits, some have rings, some have moons. The variety is astonishing. And yet, when astronomers search through this vast catalogue of exoplanetary systems, looking for systems that resemble our own solar system, systems with a protective outer gas giant and habitable zone terrestrial planets, they find very few. The statistics are striking. Of the 5,500-plus exoplanet systems discovered, approximately 15% have gas giants. Of those systems with gas giants, most have at least one gas giant in an orbit closer than Jupiter's current orbit, often much closer, sometimes orbiting their stars in only a few days. These are called hot Jupiters, and they are remarkably common in exoplanetary systems. Scientists were shocked to discover how common hot Jupiters are when exoplanets were first being discovered. Before exoplanets were detected, theorists had assumed that gas giants would form in the outer regions of planetary systems, far from their stars, just as Jupiter does in our solar system. The discovery of hot Jupiters proved this assumption wrong. Hot Jupiters are not merely rare exceptions, they are a significant fraction of planetary systems around other stars. The most likely explanation for the prevalence of hot Jupiters is that planetary migration is even more common than the grand Tack theory suggests. In many planetary systems, gas giants migrate inward and do not migrate back outward as Jupiter and Saturn did. They remain in close orbits around their stars. In some systems, migrating gas giants may have destabilized the terrestrial planets, scattering them and preventing life from developing. In other systems, migrating gas giants may have captured and destroyed the terrestrial planets that were in the habitable zone. The habitability of a planetary system is therefore strongly influenced by whether or not a large gas giant migrates through the inner planetary system and disrupts it. When astronomers search for systems that might harbor life, they look for systems with terrestrial planets in the habitable zone around a star. But they have come to realize that the presence of a terrestrial planet in the habitable zone is not sufficient for that planet to be habitable. The planet must also have protection from bombardment. It must have a configuration of other planets that prevents too many asteroids and comets from striking it, and this protection is far less common than the presence of a terrestrial planet in the habitable zone. Systems with a
terrestrial planet in the habitable zone and a protective outer gas giant in approximately Jupiter's position are quite rare. Estimates suggest that perhaps 1 to 5% of exoplanetary systems have both components. The rarity of systems with both a habitable zone terrestrial planet and a protective outer gas giant suggests that our solar system is indeed unusual. This does not mean that life cannot exist elsewhere in the universe. Certainly, other habitable planets must exist around other stars, but the specific configuration of our solar system, with Earth in the habitable zone and Jupiter providing protection from excessive bombardment, is relatively uncommon. When you combine this with all of the other requirements for habitability, the right stellar type, the right orbital distance, the presence of a moon, the presence of a protective magnetic field, and many others, the number of planets that are actually habitable becomes very small. Perhaps only a small fraction of a percent of all planets in the universe are actually suitable for complex life. The reasons why other solar systems lack protective Jupiters are manifold. In some systems, gas giants may have formed closer to their star and migrated inward even farther, remaining in close orbits. In other systems, no gas giants may have formed at all. The system may consist only of terrestrial planets or a mix of terrestrial and ice planets. In still other systems, multiple gas giants may have formed, but they may have scattered each other through gravitational interactions, leaving the system chaotic and unstable. Some systems may have had gas giants that migrated completely out of the system, ejected into interstellar space. The variety of pathways that could lead to configurations without protective Jupiters is as vast as the variety of exoplanetary systems itself. What this reveals is that the solar system, with its complement of planets in their current orbits, performing their current roles, is not a generic or inevitable configuration. It is one of many possible configurations. It is a configuration that, through a series of historical events and gravitational interactions, ended up being conducive to habitability. Other configurations would not be conducive to habitability. Some would be actively hostile to life. The fact that our solar system ended up with the configuration it has, with Earth in the habitable zone and Jupiter providing protection, seems, from the statistical perspective of looking at exoplanetary systems, to be relatively fortunate. When you realize how rare this configuration is, when you consider how many other possible configurations would not support life, you begin to grasp the fragile improbability of your own existence. You are not merely living on a habitable planet. You are living on a planet in one of the relatively rare solar systems where habitability is possible.
20. Mercury, Venus, and Mars. The neighbors that define the boundaries. We have spoken at length about Earth, and we have spoken about the outer planets that protect it. But we have not yet fully explored the role of Earth's neighboring planets, Mercury, Venus, and Mars.
These three worlds, orbiting closer to or farther from the Sun than Earth, play crucial roles in defining the boundaries of the habitable zone. They show us, through their contrasting fates, the narrow range of conditions that allow habitability. They are not merely distant neighbors, unrelated to Earth's fortune. They are essential reference points, boundary markers that define where habitability is possible and where it is not. Without these three worlds, we could not fully understand why Earth is habitable. Mercury, closest to the Sun, exists in an environment of extreme heat. The solar radiation at Mercury's distance is 10 times more intense than it is at Earth. The surface temperature reaches 430 degrees Celsius on the sunlit side. Mercury is so small and so close to the Sun that it cannot retain an atmosphere. The solar wind strips away any gases that might be released from its surface. Mercury is a barren, cratered world, with no water, no atmosphere, and no possibility of supporting life as we know it. Mercury shows us the absolute inner boundary of the habitable zone. It shows us what happens when a planet is too close to the Sun. The lesson Mercury teaches is this: even a small movement inward, toward the Sun, can have catastrophic consequences. If Earth were merely 10 or 15% closer to the Sun, we might experience conditions similar to Mercury's, or we might enter a runaway greenhouse effect similar to Venus's. Venus orbits closer to the Sun than Earth, but not drastically closer, only about 28% closer. Yet Venus is hellish. The surface temperature is 465 degrees Celsius. The atmospheric pressure is 92 times Earth's atmospheric pressure. Venus is a cautionary tale of what happens when a planet is just slightly too close to the Sun. Billions of years ago, Venus may have had oceans and a habitable climate, but as the Sun's output of energy gradually increased, Venus's climate tipped into runaway greenhouse effect. The oceans evaporated. Greenhouse gases accumulated in the atmosphere. The planet heated further. Today, Venus is an inferno. Venus teaches us that the habitable zone has sharp boundaries. You cannot be just slightly too close and still be habitable. The transition from habitable to uninhabitable is not gradual. It can be sudden and catastrophic. Mars orbits farther from the Sun than Earth, at a distance about 1.5 times Earth's distance. Mars is smaller than Earth. It is colder. Its atmosphere is thin, less than 1% of Earth's atmospheric pressure. Water cannot exist as a liquid on Mars's surface today, yet evidence suggests that Mars once had liquid water, possibly oceans, possibly even life. What happened to Mars? Mars lost its protective magnetic field. Its atmosphere was stripped away by the solar wind. The planet cooled. The habitability window closed. Mars teaches us a different lesson than Venus does. Venus warns us about being too close to the Sun. Mars warns us about being too large or too protected. A planet must be large enough to maintain a molten core and generate a protective magnetic field. A planet must have enough gravity to retain an atmosphere. Mars is too small. It lost its atmosphere. Now it is a dead world. The three neighboring planets, Mercury, Venus, and Mars, form a boundary condition around Earth. Mercury defines the inner boundary. Venus defines the upper limit of temperature tolerance. Mars defines the lower limit of planetary mass and the consequences of losing a protective magnetic field. Earth sits in the middle, in the only zone where all of these conditions are simultaneously satisfied. Earth is not merely in the habitable zone as defined by solar radiation. Earth is in the habitable zone as defined by all the conditions necessary for life. And it is surrounded by three examples of what happens when those conditions are not met. These are not coincidences. The positions and properties of Mercury, Venus, and Mars were determined by the same gravitational processes that determined Earth's position and properties. The grand Tack, the migration of the giant planets, The early dynamics of the solar system. When you look at the solar system, you see 5 inner planets, but you should see them as a system. Mercury is not independent of Earth. Venus is not isolated from Mars. They are all part of a single gravitational structure organized by the giant planets, resulting in a configuration where Earth, and only Earth, is habitable. The others serve a function. They mark the boundaries, they define the limits. They show us what Earth could become if its position were different, if its size were different, if its interior were different. In this sense, Mercury, Venus, and Mars are not merely planets. They are warnings. They are reminders. They are evidence of the fragility and uniqueness of Earth's habitability. When you stand on Earth and know that Venus burns in hellish heat just 42 million kilometers away, you are standing on a world that has narrowly escaped a fate that befell its neighbor. When you know that Mars, cold and lifeless, orbits beyond you, you are aware of what Earth might become if it were farther from the Sun, if it were smaller, if it lacked a molten core. The neighbors define the significance. They make Earth's habitability not merely a fact, but a miracle.
21. The 1-to-2 resonance between Mars and Venus. Hidden harmony. Deep within the architecture of the inner solar system, hidden from casual observation, there exists a mathematical relationship between the orbits of Mars and Venus. This relationship is not obvious. The two planets are not visible in the sky at the same time very often. Their orbits do not appear to interact in any obvious way, yet calculations reveal that their orbital periods maintain an almost perfect ratio. Venus completes approximately 1.6 orbits around the Sun for every single orbit that Mars completes. The ratio of their orbital periods is approximately 0.615, which is very close to the ratio 3:5. This near resonance is not a coincidence. It is a consequence of gravitational interactions that have persisted since the formation of the solar system. Orbital resonances occur when two bodies orbit with periods that maintain a simple integer ratio. The most famous example is the 2-to-1 resonance between Neptune and Pluto. Neptune completes 2 orbits for every 1 orbit that Pluto completes. This resonance has kept Pluto's orbit from being perturbed out of the solar system, despite numerous close gravitational encounters. The 3-to-5 near resonance between Mars and Venus is not as perfect as the Neptune-Pluto resonance, but it is close enough to have significant dynamical consequences. The near resonance means that Mars and Venus return to the same relative configurations periodically. When they do, their mutual gravitational influence is aligned in ways that tend to preserve their orbits rather than disrupting them. What does this have to do with Earth's habitability? The answer lies in understanding that the inner solar system is not composed of 4 independent planets orbiting independently around the Sun. The inner solar system is a coupled dynamical system, where each planet influences each other planet gravitationally. The orbits of the 4 terrestrial planets are not random. They are organized by resonances and near resonances that create stable and unstable regions in the orbital parameter space. Earth's orbit falls within a stable region, a region where the gravitational effects of Venus, Mars, Mercury, and the outer giant planets combine to maintain Earth's orbit in a nearly circular path around the Sun. The specific configuration of the terrestrial planets' orbits, including the near resonance between Mars and Venus, was established during the Grand Tack and the late heavy bombardment. When Jupiter and Saturn migrated, they scattered planetesimals throughout the inner solar system. The planetesimals that happened to end up in stable orbital locations persisted. Those in unstable locations were ejected or crashed into other bodies. After millions of years of bombardment and collision, the dust settled, and 4 planets remained.
Mercury, Venus, Earth, and Mars. Their orbits were not random placements. They were the surviving orbits, the orbits that remained stable after
all the gravitational perturbations, and they remained stable precisely because of their resonances and near-resonances with each other. Earth's orbit is stable, partially because of its resonances with Venus and Mars. The gravitational effects of these planets, mediated through resonances, prevent Earth's orbit from becoming too eccentric or too inclined. These effects help maintain Earth's orbit in a nearly circular path at a distance of 1 astronomical unit from the Sun. If the resonances were different, if Venus or Mars orbited at slightly different distances or with different orbital periods, the resonances would be broken. Earth's orbit might become unstable. Over millions of years, Earth might be perturbed out of the habitable zone or scattered entirely from the solar system. The profound insight here is that Earth's habitability is not determined solely by Earth itself or even by Jupiter and Saturn. It is determined by the combined gravitational effects of all the planets in the solar system, organized through a network of resonances that create stable and unstable orbital zones. Earth occupies a zone of stability created by this network. The network itself is a product of the specific history of the solar system, the Grand Tack, the late heavy bombardment, the settling of the planets into their current orbits. Change any part of this history, and the network of resonances would be different. Earth's orbit might not be stable. Habitability might not be possible. When you consider the mathematical beauty of orbital resonances, when you reflect on how the orbits of planets separated by tens or hundreds of millions of kilometers can be synchronized through gravitational forces acting across vast distances over billions of years, you begin to perceive a deep order underlying the solar system. This order is not imposed by any external intelligence. It emerges naturally from the laws of physics and gravity. But the fact that this order results in a configuration where Earth is habitable seems almost too perfect to be accidental. It suggests that there is something fundamental about the structure of our solar system that we do not yet fully understand. Something that connects the microscopic to the macroscopic, the atomic to the cosmic, the individual to the universal.
22. Earth's near-perfect circular orbit. Accident or design? Most people think of planetary orbits as perfectly circular. In elementary school, we are shown diagrams with planets orbiting the Sun in neat circular paths, like beads on invisible strings. In reality, planetary orbits are ellipses, not circles. An ellipse is a circle that has been stretched, flattened along one axis. The degree to which an ellipse is flattened is called its eccentricity. A perfect circle has an eccentricity of 0. The more eccentric an orbit is, the more elongated it becomes. Earth's orbit has an eccentricity of approximately 0.0167. This is a very small number. It means that Earth's orbit is very nearly circular, only slightly flattened. In fact, Earth's orbit is one of the most circular orbits among all the planets in the solar system. Mercury's orbit, by contrast, has an eccentricity of 0.206, making it much more elliptical. Why does Earth's nearly circular orbit matter? Because a circular orbit produces stable temperatures and climate. As Earth orbits the Sun, the distance between Earth and the Sun varies slightly due to the ellipticity of the orbit. Earth's closest approach to the Sun, called perihelion, occurs in early January. At perihelion, Earth is approximately 147.1 million kilometers from the Sun. Earth's farthest distance from the Sun, called aphelion, occurs in early July. At aphelion, Earth is approximately 152.1 million kilometers from the Sun. The difference is about 5 million kilometers, approximately 3.3% of Earth's average distance. This variation means that Earth receives about 7% more solar radiation at perihelion than at aphelion. If Earth's orbit were much more eccentric, if perihelion were much closer to the Sun and aphelion much farther, the variation in solar radiation would be much larger. If the variation were large enough, it would create extreme seasonal variations. Some regions of Earth might experience baking summers when at perihelion and freezing winters when at aphelion. The climate would be unstable and harsh. Life would be pushed to extinction repeatedly. But Earth's orbit is not very eccentric. It is nearly circular. The variation in solar radiation is only about 7%. The climate remains relatively stable over geological timescales. This stability has allowed life to flourish and evolve into complex forms. How did Earth's orbit become so nearly circular? The answer involves gravitational interactions with other planets over billions of years. In the early solar system, Earth's orbit might have been more eccentric. It might have been perturbed by gravitational interactions with Venus, Mars, and the giant planets. But these same interactions that might have made the orbit more eccentric also had a damping effect. Over time, through a process called dynamical friction, the eccentricity of Earth's orbit was reduced. Dynamical friction occurs when a body orbiting in a gravitational system experiences repeated small perturbations from other bodies. These perturbations, if they act coherently over long periods of time, can damp out the orbit's eccentricity, making it more circular. The remarkable thing is that Earth's orbit ended up with just the right amount of eccentricity to be stable, but not so circular that the system became unstable. If Earth's orbit were perfectly circular with zero eccentricity, it might actually be less stable than it currently is. The small eccentricity provides a buffer against perturbations. But if Earth's eccentricity were much larger, the stability would be compromised in a different direction, through excessive seasonal temperature variations. Earth's current eccentricity appears to be in a Goldilocks zone. Not too small, not too large, but just right. The near-perfect circularity of Earth's orbit is therefore not a trivial detail. It is a consequence of billions of years of gravitational interactions, and it is essential for Earth's habitability. The combined gravitational effects of Venus, Mars, Mercury, Jupiter, Saturn, Uranus, and Neptune all play roles in maintaining Earth's orbital eccentricity at its current value. If any of these planets were slightly different in mass or position, Earth's orbital eccentricity might be different. Life would face different challenges. The climate would be less stable. The biosphere might not have had time to evolve the diversity we see today. When you consider the vast number of variables that had to align just right, the masses of all the planets, their initial positions, their migration histories, the resonances between their orbits, to produce Earth's nearly circular orbit, the improbability becomes staggering. Yet here Earth is, orbiting in a path so nearly circular that we can hardly perceive the difference. And this near-perfect circularity is one of the key factors that makes life on Earth possible. The other planets, through their gravitational influences accumulated over billions of years, have conspired to maintain Earth's orbit in this near-perfect state. They have done this work silently, invisibly, without any awareness or intention. And yet, the result is perfect. 23. The Moon and Axial Tilt, the silent stabilizer. Earth rotates on an axis inclined at approximately 23.5 degrees relative to the plane of its orbit around the Sun. This inclination is the reason we have seasons. When Earth's northern hemisphere tilts toward the Sun, it is summer in the north and winter in the south. 6 months later, when the southern hemisphere tilts toward the Sun, the seasons reverse. This axial tilt is crucial for life. It creates seasonal variations in temperature and sunlight that have driven the evolution of countless adaptations in organisms. Plants that go dormant in winter and bloom in spring. animals that migrate seasonally, ecosystems that pulse with the rhythm of the seasons. Without the axial tilt, there would be no seasons. The equator would receive more solar radiation than the poles. Heat would distribute very unevenly. Climate would be harsher and less suitable for complex life. But here is what most people do not realize. Earth's axial tilt does not remain perfectly constant. It precesses. It slowly wobbles like a spinning top that is gradually slowing down. The wobble is very slow. A complete precession takes approximately 26,000 years. But over geological timescales, this wobble matters. The wobble causes the orientation of Earth's rotational axis to change gradually. Over thousands of years, the North Star, the bright star that appears directly above Earth's North Pole, changes. Currently, Polaris serves as the North Star, but 12,000 years ago, the North Star was Vega. In another 12,000 years, it will be different again. The wobbling is called precession, and it is caused by the gravitational torque exerted by the Sun on Earth's equatorial bulge. Earth is not a perfect sphere. It bulges slightly at the equator due to its rotation. This bulge has mass, and the Sun's gravity pulls on this mass. This pull exerts a torque that causes Earth's axis to precess. The precession caused by the Sun's gravity alone would cause Earth's axis to wobble, but this wobble would be much larger than it actually is. The Moon exerts a tremendous stabilizing effect on Earth's axial tilt. The Moon's gravity also exerts a torque on Earth's equatorial bulge, but because the Moon orbits Earth, rather than remaining at a constant position, the Moon's gravitational torque averages out over time to partially cancel the Sun's torque. The result is that Earth's axial tilt precesses much more slowly than it would without the Moon's stabilizing influence. The Moon essentially holds Earth's axis steady, preventing it from wobbling too much. Without the Moon, Earth's axis would precess much more rapidly. Earth's axial tilt would change significantly over timescales of thousands or tens of thousands of years, rather than hundreds of thousands of years. What would this mean for habitability? Scientists have calculated the effects using computer simulations of Earth's climate and orbital dynamics. Their conclusions are striking. Without the Moon's stabilizing influence, Earth's axial tilt would vary wildly between approximately 0 degrees and approximately 60 degrees over periods of millions of years. Such variations would be catastrophic for climate stability. When the axial tilt approaches 0, the equator receives more solar radiation and the poles receive less. The climate becomes more extreme, with hot equatorial regions and cold polar regions. When the axial tilt approaches 60 degrees, the poles receive more direct solar radiation and the equator receives less. The climate becomes inverted. Some regions experience extreme heat, others experience extreme cold. Complex life evolves to adapt to current climate conditions. But if the climate changes dramatically every few million years, complex life cannot keep pace. Species go extinct faster than new species can evolve. The biosphere would be driven to simplicity. Only the hardiest, most adaptable organisms would survive. The Moon's stabilization of Earth's axial tilt is therefore not a minor detail in Earth's climate system. It is essential for climate stability over geological timescales. And this stabilization has been maintained for billions of years through the Moon's consistent gravitational interaction with Earth. The Moon was created by the giant impact, an event whose probability was extraordinarily low. If that impact had not occurred, if the Moon had not formed, Earth's axial tilt would be chaotic and unstable. Complex life would not have evolved. You would not exist. The stability that you enjoy, the predictable seasons, the climate variations that organisms have adapted to, the long periods of relative stability that have allowed complex ecosystems to develop. All of this flows directly from the Moon's presence
and its gravitational stabilization of Earth's axis. When you look at the moon in the night sky, you are looking at a body that does far more than merely light the darkness. The moon is your silent guardian, your climate stabilizer, the body that has maintained the conditions necessary for life to flourish for 4 billion years. The moon exerts its influence not through dramatic, visible actions, but through subtle, gravitational effects that accumulate over epochs. This is the pattern we have observed repeatedly in our exploration of the solar system. The planets and moons do not merely exist passively in their orbits. They actively influence and maintain the conditions necessary for habitability through gravitational interactions, resonances, and coordinated orbital mechanics that span billions of kilometers and billions of years.
24. Milankovitch cycles, when planetary orbits influence climate rhythms. When geologists drill deep into Earth's crust and extract long cores of ice and sedimentary rock, they find something remarkable layered within the geological record. The composition of the rocks and the isotopic ratios of elements change in patterns. Ice cores show variations in oxygen isotopes that reflect the temperature at the time the ice formed. Sedimentary rock layers show variations in the organisms that lived during different periods. When scientists date these layers and analyze the patterns, they discover that Earth's climate has varied in periodic cycles. Ice ages come and go. Warm periods alternate with cold periods. And the timing of these cycles, the lengths of the cycles, and their regular recurrence matches the cycles of variations in Earth's orbital parameters caused by gravitational interactions with other planets. In the 1920s, a Serbian astronomer named Milankovitch made a calculation that would revolutionize our understanding of climate cycles. He calculated how Earth's orbital eccentricity, axial tilt, and precession vary over tens of thousands of years due to gravitational interactions with other planets. He then calculated how these variations would affect the distribution of solar radiation hitting Earth's surface. Finally, he proposed that these variations in solar radiation would cause variations in climate, ice ages during periods when Earth's orbit reduces solar radiation hitting the poles, and warm periods during times when solar radiation is at a maximum. Milankovitch's theory explained the periodic climate variations observed in geological records. The theory became known as the Milankovitch cycles, or the astronomical theory of climate. The 3 primary Milankovitch cycles are eccentricity, axial tilt, and precession. The eccentricity cycle, caused primarily by gravitational interactions between Earth and Jupiter, has a period of approximately 100,000 years. During this cycle, Earth's orbital eccentricity varies from nearly 0 to approximately 0.06. When the eccentricity is low, Earth's orbit is nearly circular, and the variation in solar radiation between perihelion and aphelion is small. When the eccentricity is high, Earth's orbit is more elliptical, and the variation in solar radiation is greater. The axial tilt cycle, caused by gravitational interactions between the Sun, Moon, and other planets, has a period of approximately 41,000 years. Earth's axial tilt varies between approximately 22.1 degrees and 24.5 degrees over this cycle. The precession cycle, caused by the gravitational torque of the Sun and Moon on Earth's equatorial bulge, has a period of approximately 26,000 years. During this cycle, the direction of Earth's axis gradually rotates, causing the North and South poles to trace a circle in the sky. These 3 cycles combine to create complex patterns of solar radiation variations that drive climate changes on Earth. When all 3 cycles align, when the eccentricity is high, the axial tilt is steep, and the precession is positioned such that the northern hemisphere experiences maximum solar radiation in summer, the result is an exceptionally warm period. When the cycles align differently, when eccentricity is low, tilt is shallow, and precession is positioned to minimize solar radiation in the northern hemisphere summer. The result can be a period of glaciation. The most recent glacial maximum, when ice sheets covered much of North America and Europe, occurred approximately 20,000 years ago. The transitions between glacial and interglacial periods, the waxing and waning of ice sheets, correlate remarkably well with the predictions of Milankovitch theory. What is most fascinating about Milankovitch cycles is that they are not autonomous climate processes. They are directly driven by the gravitational interactions between planets. The 100,000-year eccentricity cycle is caused by Jupiter's gravity. The 41,000-year axial tilt cycle is caused by the combined effects of the Sun's gravity and the Moon's stabilizing influence. The 26,000-year precession cycle is caused by the Sun's and Moon's gravitational torques on Earth's equatorial bulge. In other words, the climate rhythms that have shaped the evolution of life on Earth over the past few million years are directly connected to the orbits and masses of the other planets. Jupiter influences Earth's climate cycles. The Moon influences Earth's climate stability. Mars influences Earth's orbital eccentricity through its gravitational interactions. Earth's climate is not determined solely by processes on Earth. It is determined by the entire planetary system. Life on Earth has adapted to these Milankovitch cycles. Organisms have evolved to respond to the periodic climate variations. Plants and animals that can survive warm periods also evolve mechanisms to survive cold periods. Migration, hibernation, dormancy, these are adaptations that evolved in response to the predictable climate cycles driven by Milankovitch effects. The biodiversity we see on Earth is not merely the result of millions of years of random mutation and natural selection. It is shaped by the predictable climate cycles that result from gravitational interactions between planets. In a real sense, life on Earth has been sculpted by Jupiter's gravity, by the Moon's influence, by the orbital dynamics of the entire solar system. The creatures that fill our world, the whales in the oceans, the eagles in the sky, the forests covering the land, all exist in the form they do because of Milankovitch cycles. They exist because of the subtle gravitational coordination between planets that produces reliable climate patterns over timescales of thousands and tens of thousands of years.
25. Exoplanet discoveries, showing us how rare we truly are. Before 1995, humanity had knowledge of 9 planets in the solar system and no others. We could only speculate about whether planets orbited other stars. We could imagine distant worlds bathed in alien light, but we had no evidence that such worlds existed. Then, in October of 1995, the astronomers Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b, a planet orbiting the star 51 Pegasi, approximately 47 light-years from Earth. This discovery opened a floodgate. Within months, additional exoplanets were discovered. Within years, dozens. Within decades, thousands. Today, more than 5,500 exoplanets have been catalogued around stars in our galaxy. The discovery of exoplanets has revolutionized our understanding of planetary systems, and more importantly, has provided crucial context for understanding Earth's uniqueness. The exoplanets discovered so far represent an astonishing diversity of configurations. Some systems have multiple gas giants orbiting very close to their star, in configurations astronomers initially thought impossible. These are the hot Jupiters, planets the size of Jupiter orbiting their stars in just a few days, bathed in intense radiation, their atmospheres likely being stripped away by the stellar wind. Other systems have terrestrial planets in orbits so close to their stars that the surface temperature would melt lead. Still other systems have terrestrial planets in the habitable zone,
orbiting at distances where liquid water could theoretically exist on the surface. But even the discovery of exoplanets in habitable zones does not guarantee habitability. The planets might lack atmospheres. They might have no magnetic field to protect them from stellar radiation. They might lack moons to stabilize their climate. They might be tidally locked, with one face always pointing toward their star and the other always facing away. When astronomers analyze the exoplanet data statistically, searching for systems that might resemble our own solar system, the results are sobering. Of the 5,500-plus exoplanets discovered, approximately 15% are in systems with multiple planets. Of those, only a small fraction have planetary architectures that resemble the solar systems. The solar system has a specific structure. Terrestrial planets in the inner region, a habitable zone terrestrial planet, Earth, and protective gas giants in the outer region. This structure is quite rare among known exoplanetary systems. Most systems either have no gas giants or have gas giants positioned in the inner region, the hot Jupiters, or have configurations that would be unstable or unsuitable for life. When astronomers search for exoplanetary systems with both a habitable zone terrestrial planet and a protective gas giant in approximately Jupiter's position, they find that only perhaps 1 to 5% of systems meet these criteria. The rarity of systems with Earth-like
configurations is not merely an interesting statistical fact. It has profound implications for how we understand our place in the universe. It means that the solar system is not a generic, inevitable configuration. It is an unusual configuration, one that appears less frequently than randomly distributed planetary systems would predict. It means that Earth is not merely a habitable planet. It is a planet within a habitable system, a system whose structure is conducive to habitability. It is the combination of factors: Earth's position in the habitable zone, Earth's appropriate size, Earth's protective magnetic field, Earth's stabilizing moon, and the protective configuration of the outer planets, all working together, that makes life on Earth possible. Remove any one of these factors, and habitability might cease. The distribution of exoplanets also reveals the diversity of pathways that planetary systems can take. Some systems form with more planets than the solar system has. Some form with fewer. Some lose planets to collisions or gravitational ejections. Some capture planets from other systems. The diversity suggests that the formation of planetary systems is a complex, often chaotic process. The solar system's current structure is therefore not inevitable. It is one of many possible outcomes. The fact that it is an outcome that produces habitability is remarkable. The fact that it appears to be relatively rare among exoplanetary systems makes it even more remarkable. When you consider this rarity, when you contemplate the billions of other planetary systems in just our galaxy alone, and trillions of other galaxies beyond our own, you begin to grasp the profound improbability of your own existence. The discovery of exoplanets has also revealed something about the process of planetary migration. We discussed the grand Tack theory earlier, the proposal that Jupiter migrated inward and then outward in the early solar system. This theory seemed highly speculative until exoplanet observations provided evidence that planetary migration is real and common. Many exoplanetary systems show evidence of planetary orbital arrangements that could only have resulted from migration. Hot Jupiters orbiting close to their stars are believed to be the result of inward migration followed by the failure to migrate back outward. The existence of hot Jupiters proves that planetary migration occurs. And if the grand Tack migration occurred in the early solar system, as we believe it did, then the current configuration of the solar system, with Earth in the habitable zone and protected by outer giant planets, is directly attributable to this migration.
The structure of the solar system that allows life is the direct consequence of Jupiter's early journey through the solar system.
26. Computer simulations, revealing the fragility of planetary stability. In the late 20th century, as computers became more powerful and mathematicians developed sophisticated algorithms for calculating gravitational dynamics, a new tool became available to planetary scientists: computer simulations of planetary motion. These simulations could track the orbits of planets over millions or billions of years, accounting for the gravitational interactions between all the bodies in a system. They could test hypotheses about planetary formation and stability. They could answer counterfactual questions. What would happen if a planet were positioned differently? What if it were more massive? What if it were missing entirely? These simulations have become crucial tools for understanding why the solar system has its current structure and what might destabilize it. When researchers run simulations of the solar system, starting with the current positions and masses of the planets and calculating forward billions of years, they find that the solar system remains stable. The planets continue in their orbits. Earth remains in the habitable zone. No catastrophic collisions occur. This is good news. It means that the solar system, as it currently is configured, should remain habitable for billions of years into the future. But when researchers run simulations with slightly altered initial conditions, the results are often dramatically different. If Jupiter's mass were 10% larger, simulations show that the inner solar system becomes chaotic within millions of years. If Jupiter's position were 10% closer to the Sun, similar chaos results. If Saturn were in a different orbit, or if Mars were more massive, or if any of dozens of other parameters were slightly different, the stability could be disrupted. These findings have a name in planetary science: the Fragile Solar System Hypothesis. The hypothesis proposes that the solar system is in a state of delicate stability. It is stable as it currently is configured, but only narrowly stable. Small perturbations to the initial conditions, the masses of the planets or their positions, would lead to instability. This is different from an assumption that the solar system is robustly stable, that it would remain habitable despite significant variations in planetary parameters. The Fragile Solar System Hypothesis suggests that we exist in a configuration that represents a narrow, stable window. We are fortunate that the parameters fell into this narrow window. Had they fallen slightly outside, the solar system would be chaotic and Earth would not be habitable. One particularly striking simulation involves the Lyapunov time of the solar system, a measure of how long it takes for small uncertainties in initial conditions to grow into large uncertainties in predicted outcomes. For the solar system, the Lyapunov time is on the order of tens of millions of years. This means that if we were to measure the position and velocity of every planet with perfect precision today, and then calculate the state of the solar system 100 million years in the future, tiny uncertainties in our measurements would grow to become very large uncertainties in the predicted positions. We would not be able to accurately predict the future configuration of the solar system beyond about 100 million years. The solar system is chaotic in the technical sense. Small perturbations grow exponentially over time. Yet, despite this chaos on long timescales, the solar system remains habitable. This suggests that the region of stability, the region of parameter space where the solar system remains habitable, has a certain size and structure that keeps Earth's orbit within it, despite the ongoing chaos. The Fragile Solar System Hypothesis has important implications for the prevalence of habitable planets elsewhere in the universe. If the solar system's stability is fragile, if it occupies a narrow, stable window, then other planetary systems would also need to occupy narrow, stable windows to be habitable. This would make habitable systems relatively rare. In fact, when we compare the statistical distribution of exoplanetary systems to the predictions of the Fragile Solar System Hypothesis, we find good agreement.
Exoplanetary systems with configurations similar to the solar systems are indeed relatively rare. Systems in narrow, stable windows are less common than systems in more broadly stable configurations, or systems that are unstable. The rarity of exoplanetary systems resembling the solar system may be explained by the rarity of narrow, stable windows. These computer simulations have also been used to study the aftermath of the late heavy bombardment. When researchers run simulations of the solar system, beginning with a configuration predicted to exist just before the Grand Tack migration, and they simulate the migration events, they can reproduce the key features of the early solar system and the subsequent clearing of the bombardment. The simulations show that the current configuration of the solar system, with Earth positioned where it is in a stable orbit in the habitable zone, is the natural outcome of the Grand Tack migration and the subsequent settling of the planets into their current positions. But they also show that other outcomes were possible. If parameters had been slightly different, different configurations would have resulted, and many of those configurations would not support habitability.
27. The Fermi paradox. If planets are common, where is everybody? The Fermi paradox. If the universe contains billions of galaxies, each containing billions of stars, and if many of those stars have planets, then the universe must contain an enormous number of planets. Some of those planets would likely be habitable. Some would likely have life. Some would likely have intelligent life. The civilizations on those worlds would build spacecraft and radio transmitters. They would expand across their star systems and perhaps venture into interstellar space. Yet when we look at the night sky, when we listen with radio telescopes for signals from extraterrestrial civilizations, we hear only silence. We see no megastructures indicating the presence of advanced alien civilizations. We detect no signals. The universe seems empty of intelligent life, other than ourselves. Fermi's question became known as the Fermi paradox. If intelligent life is common, where is everybody? Scientists have proposed many explanations for the Fermi paradox. Perhaps intelligent life is short-lived, destroying itself through war or environmental collapse before it can spread across the galaxy. Perhaps intelligent life is common, but civilizations are separated by such vast distances that communication is impossible. Perhaps intelligent life does exist elsewhere, but it is currently far away from Earth, and the light speed limit on travel means we will never meet. Perhaps our current state of technology is simply too primitive to detect the presence of advanced civilizations. Perhaps we are listening at the wrong frequencies or using the wrong methods. But there is another possible explanation, one that flows directly from our understanding of planetary habitability. Perhaps intelligent life is far rarer than we initially assumed. The discovery of exoplanets has revolutionized our understanding of planetary prevalence. We now know that planets are very common. It is estimated that the Milky Way galaxy alone contains at least 100 billion planets, and possibly trillions. But planets are not the same as habitable planets, and habitable planets are not the same as life-bearing planets, and life-bearing planets are not the same as planets with intelligent life. Each step in this progression involves a dramatic reduction in numbers. If we assume that 10% of planets are in habitable zones around stars suitable for life, a generous estimate, then the Milky Way would contain roughly 10 billion habitable planets. But if only 1% of habitable planets actually have life, due to the difficulty of abiogenesis, the process by which non-living chemistry becomes living biology, then there would be roughly 100 million life-bearing planets. And if only 1% of life-bearing planets develop intelligent life, then there would be only 1 million civilizations in our galaxy. But these are still generous estimates.
The evidence we have from exoplanet observations suggests that habitable zone planets orbiting in systems with protective outer gas giants
are much rarer than 10% of all planets. If such systems are only 1% of all planets, then habitable planets would be roughly 100 million in the entire galaxy. And if only 1% of those have life, there would be only 1 million life-bearing planets. And if only 0.1% of those have intelligent life, there would be only 1,000 advanced civilizations in the galaxy. In a galaxy of 200 billion stars, 1,000 civilizations are so widely separated that communication would be virtually impossible. This is one possible resolution to the Fermi paradox. Intelligent life is so rare that civilizations are typically separated by thousands of light years, making contact impossible. The reason intelligent life might be so rare is precisely what we have been discussing. Habitability is far rarer than it initially appears. A planet must not merely be in the habitable zone, it must be in a system with the right structure. Protective outer gas giants, stable inner planets, appropriate moons, protective magnetic fields. It must have the right composition to produce a magnetic field and an atmosphere. It must be the right size. It must have had the right history. It must have survived the late heavy bombardment and the chaos of the early solar system to reach a stable state where life can flourish. And life, once it emerges, must have stable conditions to evolve into intelligent forms. Complex life requires billions of years to evolve. If the planet experiences repeated extinction events due to asteroid impacts or climate instability, intelligence may never develop. The combination of all these factors, the rare system structure, the right planetary parameters, billions of years of stable evolution, may make intelligent life incredibly rare in the universe. If intelligent life is incredibly rare, then the Fermi paradox is resolved. We are not hearing signals from alien civilizations because there are very few advanced civilizations in our galaxy, and they are very far apart. We are not merely in a habitable world, we are in one of the rare worlds where intelligent life has emerged. And the reason we are here, the reason we have evolved the capacity to contemplate the stars and ask why the universe seems empty, is because the solar system has proven to be an exceptionally stable, unusually habitable environment. It is an environment that resulted from billions of years of fortunate cosmic events. The grand Tack, the moon-forming impact, the stabilization of Earth's orbit and axial tilt, the protection offered by the outer planets. These events, each improbable in itself, combined to produce a world where intelligent life could arise. We are not common. We are extraordinary.
28. Earth's future. How long will the Sun preserve our habitability? The Sun is a star, and like all stars, it is slowly burning itself out. The Sun fuses hydrogen into helium in its core. This fusion process releases energy that has powered life on Earth for 4.6 billion years. But this process cannot continue forever. The Sun has a finite supply of hydrogen. It will eventually exhaust this supply. When the Sun has exhausted its core hydrogen, the core will contract and heat up. The outer layers will expand, and the Sun will become a red giant. This transformation will take billions of years from now, but when it occurs, it will be catastrophic for life on Earth. The Sun's surface will expand outward, possibly engulfing Mercury and Venus, and certainly rendering Earth uninhabitable. But before the Sun becomes a red giant, it will gradually increase in brightness, according to a process called the faint young sun paradox resolution. The Sun is actually getting hotter and brighter as it ages, at a rate of about 10% brighter every billion years. This gradual brightening will eventually render Earth uninhabitable, long before the Sun becomes a red giant. In approximately 1 to 2 billion years, the Sun will be so bright that Earth's surface temperature will rise dramatically. The greenhouse effect will intensify. The climate will warm. At some point, the oceans will begin to evaporate.
The water vapor will trap heat in the atmosphere, creating a runaway greenhouse effect similar to Venus's. Within a billion years, or perhaps a few billion years, Earth will become too hot to support complex life. The biosphere will be driven to extinction. Earth will become a lifeless rock, a twin of Venus, barren and lifeless. This is the inevitable fate of Earth, given enough time. The Sun will eventually make Earth uninhabitable, but a billion years is an extraordinarily long time. On a human timescale, it is incomprehensible. It is millions of times longer than human civilization has existed. It is longer than all of human history, longer than all of the time humans have walked on Earth, times a billion. Life has 1 to 2 billion years remaining on this world, assuming humanity does not destroy it sooner. In that time, billions of species could evolve and go extinct. Entire planetary biospheres could rise and flourish. Civilizations could rise and fall. And if humanity is wise, if we develop the technology and the wisdom to survive and flourish, we might expand to other worlds before Earth becomes uninhabitable. We might terraform Mars, transforming it from a cold, dry desert into a habitable world. We might establish settlements on the moons of Jupiter and Saturn in the outer solar system, where the sun's brightness will be less relevant. We might even venture to other star systems, becoming a spacefaring civilization. The question of how long habitability will persist on Earth is directly related to the other planets and the overall structure of the solar system.
The Sun's evolution will eventually make Earth uninhabitable. But before that happens, in the time remaining, the other planets will continue to play their roles. Jupiter will continue to protect Earth from impacts. Saturn will continue to maintain the resonances that keep the inner solar system stable. The Moon will continue to stabilize Earth's axial tilt. The other terrestrial planets, Mercury, Venus, and Mars, will continue to define the boundaries beyond which habitability cannot extend. They will provide context for understanding the narrow range of conditions that allow life. And, in understanding that context, future generations of humans, if we survive, will understand the profound improbability and preciousness of our world. The fact that the Sun will eventually destroy the habitability of Earth adds urgency to our current moment. We live in a window of habitability. The conditions on Earth that allow life have persisted for billions of years because of the stability of the solar system and the protection offered by the other planets. But this window will not remain open forever. Eventually, the Sun will close it. This does not mean we should despair. Rather, it should inspire us to appreciate the gift we have been given, billions of years of stable, habitable conditions. It should inspire us to preserve and nurture the biosphere, and it should inspire us to develop the wisdom and technology to extend habitability beyond Earth if we can, to carry life to other worlds, and perhaps ensure that consciousness, the universe's way of knowing itself, persists beyond the lifetime of Earth. The other planets have given us this time. What we do with it is up to us.
29. Resilience and regulation. Earth as a self-maintaining system. One of the most profound insights in Earth science is the realization that Earth itself is not a passive stage upon which life performs. Rather, life and geology interact in complex feedback loops that maintain conditions suitable for life. This concept has been formalized in what is called the Gaia hypothesis, proposed by the scientist James Lovelock in the 1970s. The hypothesis suggests that Earth's biosphere, geology, and atmosphere form an integrated system that actively maintains conditions suitable for life. The system is self-regulating, like a living organism. When conditions drift away from optimal, biological and geological processes act to restore them. This is not conscious regulation. There is no goal or intention. Rather, it emerges from the mathematical properties of coupled feedback systems.
One example of such regulation is the carbon cycle. Carbon dioxide in the atmosphere acts as a greenhouse gas, trapping heat. If the amount of CO2 increases, the greenhouse effect strengthens and the climate warms. But warming triggers chemical weathering of rocks, a process where rainwater reacts with silicate minerals, breaking them down and removing CO2 from the atmosphere. Over millions of years, this process reduces atmospheric CO2, cooling the climate. Conversely, if the amount of CO2 decreases, the climate cools. Less chemical weathering occurs. CO2 accumulates in the atmosphere. The climate warms again. The system oscillates around an equilibrium. This feedback loop has maintained Earth's climate within a range suitable for life for billions of years, despite the gradual brightening of the sun and massive changes in the composition of the atmosphere. Another example involves biological processes. Over the past 2.4 billion years, photosynthetic organisms have been accumulating oxygen in the atmosphere. This oxygen reacts with methane, a potent greenhouse gas. As methane is oxidized by oxygen, it is removed from the atmosphere. The greenhouse effect weakens, and the climate cools. But cooling reduces the rate of biological processes that produce methane, slowing the removal of methane from the atmosphere. The system reaches a balance. The amount of oxygen in the atmosphere is maintained at levels suitable for complex life, approximately 21%. This is not accidental. If oxygen were much higher, say 25%, spontaneous fires would ignite everywhere on Earth, and ecosystems would be destroyed. If oxygen were much lower, say 15%, complex life would have insufficient respiratory capacity. The atmosphere maintains oxygen at the optimal level through biological processes regulated by feedback mechanisms. These examples of regulation suggest that Earth possesses a form of resilience. Perturbations from outside can push the system away from equilibrium, but internal feedback mechanisms act to restore equilibrium. However, this resilience is not unlimited.
If a perturbation is large enough or fast enough, it can overwhelm the system's capacity to regulate. The late heavy bombardment is an example. The impacts were so violent and so frequent that they disrupted the normal processes of regulation. Yet somehow, life persisted, possibly in protected environments like hot springs or underground aquifers. And after the bombardment ended, after stability returned, life flourished and rediversified. This suggests that resilience is not absolute. It can be exceeded, but it is also more robust than we might expect. The resilience and regulatory capacity of Earth add a layer of complexity to our understanding of habitability. It is not sufficient that a planet be in the right orbit with the right composition. The planet must also have the capacity to regulate its own conditions over geological timescales. Without this capacity, Earth would have drifted either into a runaway greenhouse like Venus or into a frozen snowball. The regulatory capacity of Earth is dependent on the presence of a biosphere and on the geological processes driven by the planet's internal heat and chemical cycling. It is therefore a property that emerged slowly over billions of years, as life colonized the planet and developed ever more complex ways of influencing the abiotic environment. The other planets do not have this capacity. Mars cannot regulate its climate because it lost its magnetic field in its atmosphere. Venus cannot regulate because it entered a runaway greenhouse from which escape is impossible. But Earth can, and has, maintained conditions suitable for life through the interplay of biological and geological processes. 30. The privileged observer, recognizing our exceptional position. There is a philosophical principle called the Copernican principle, named after the astronomer Nicolaus Copernicus, who challenged the geocentric model of the universe. The Copernican principle states that Earth and humanity do not occupy a special or privileged position in the universe. We are not the center of the cosmos. We are not unique or exceptional. We are ordinary. This principle has been profoundly useful in science. It has prevented us from making speculative assumptions about our importance. It has encouraged humility. It has led us to search for universal principles that apply everywhere, not just on Earth. But, as we have explored the habitability of Earth in the context of the solar system, a more nuanced view emerges. While it is true that we are not at the center of the universe, it is equally true that we occupy an exceptionally habitable world in an exceptionally well-structured planetary system. The evidence for this exceptionality is overwhelming. We have discovered thousands of exoplanets, and we have found that Earth-like worlds in well-protected, stable systems are relatively rare. We have developed computer simulations of planetary dynamics, and we have found that the solar system is in a state of delicate stability that might easily have been disrupted. We have studied the geological and biological history of Earth, and we have found that habitability depends on a long chain of improbable events. The giant impact that formed the Moon, the grand Tack migration that organized the solar system, the late heavy bombardment that sterilized but did not destroy life, the eventual emergence of a magnetic field and an oxygen-rich atmosphere. Each of these events was improbable. Their combination is extraordinarily improbable, yet they all occurred. The realization that we occupy an exceptional world is not a violation of the Copernican principle, rather, it is a refinement of it. The Copernican principle is correct in saying that we are not at the center of the universe, but it does not say that all worlds are identical or all regions of space are equally habitable. Some regions are habitable, others are hostile, and we happen to occupy one of the habitable regions. This is not a contradiction, it is a truth that coexists with the Copernican principle. In mathematics, this is sometimes called the observer selection effect, or the anthropic principle. The principle states that we should not be surprised to find ourselves in a region of the universe that is compatible with our existence. We could not find ourselves anywhere else, because we would not exist anywhere else. But this does not mean that all regions are equally habitable. It means that we will naturally find ourselves in one of the habitable regions. When we contemplate our position, we are not merely observers of a random cosmos. We are observers in an exceptionally well-organized system. We are
Inhabitants of a world whose habitability flows from a vast, coordinated effort performed by multiple planets, billions of kilometers apart, acting through gravity across billions of years. We are the product of improbable events. We are the beneficiaries of cosmic architecture. We are, in a very real sense, privileged. This privilege comes with responsibility. If we are aware that we occupy an exceptional world, a world whose habitability is precarious and depends on the maintenance of certain conditions, then we have a responsibility to preserve those conditions. We have a responsibility to preserve the climate, the magnetic field, the biosphere, the conditions that allow life to flourish. This understanding transforms our relationship with Earth. We do not merely live on a rock that happens to orbit a star. We live in an intricate system, a cosmic harmony, where every component plays a vital role. The Moon holds our climate stable. Jupiter sweeps away asteroids that would otherwise strike us. The Sun provides energy. The other terrestrial planets define the boundaries beyond which habitability cannot extend. And within this system, within this orchestrated arrangement of celestial bodies, life has emerged and flourished. We are not observers of this system from outside. We are part of it. We emerge from it. We are made of the same matter as the other planets. We are organized by the same gravity that organizes the solar system. We are conscious expressions of the universe aware of itself. And that is an exceptional privilege.
31. The responsibility of consciousness, preserving the habitable world.
For billions of years, Earth was habitable but unconscious. Life existed, flourished, evolved into ever more complex forms, but there was no awareness. There was no consciousness contemplating the universe. Then, approximately 300,000 years ago, consciousness emerged in the form of human beings on the African continent. Consciousness gave humanity the ability to understand the universe, to perceive patterns, to recognize the improbability of our existence. But consciousness also brought something else: the capacity to change our environment in profound ways. For the first time in Earth's history, a species could deliberately reshape the planet. A species could build structures visible from space. A species could alter the atmospheric composition. A species could drive other species to extinction, deliberately or accidentally. Consciousness was a new force in the cosmos, capable of both preserving and destroying habitats. For most of human history, the impact of conscious beings on the planet was limited. A few million humans could not significantly alter planetary climate or atmosphere. But in the last few centuries, especially the last few decades, human population and technological power have grown exponentially. Today, nearly 8 billion humans inhabit the planet. We burn fossil fuels, releasing carbon dioxide that was buried for millions of years. We clear forests, destroying habitats. We emit greenhouse gases. We create pollution. We alter ocean chemistry. We are changing the planetary climate at a rate faster than it has changed in millions of years. We are conducting an unintended experiment on the only habitable world we know. The question we now face is whether the regulatory and resilience systems that have maintained habitability for billions of years can accommodate the changes we are causing. The scientific evidence is clear. We have already changed the climate. Global average temperatures have risen approximately 1.1 degrees Celsius since the pre-industrial era. Ice sheets are melting. Sea levels are rising. Weather patterns are shifting. Ecosystems are being disrupted. Species are going extinct at rates higher than any time since the extinction that killed the dinosaurs 66 million years ago. These changes are driven primarily by human activity, the burning of fossil fuels being the single largest contributor. The evidence is so overwhelming that 97% of climate scientists agree that human-caused climate change is occurring. We are not merely observing changes, we are causing them. Consciousness has become a geological force, shaping the planet as profoundly as plate tectonics or asteroid impacts once did. But consciousness brings not only the capacity to cause harm, it brings the capacity to choose a different path. We can reduce our greenhouse gas emissions. We can transition to renewable energy. We can preserve ecosystems and protect biodiversity. We can develop technologies that sequester carbon from the atmosphere. We can choose to live within the planetary boundaries that allow life to flourish. The fact that we face a choice is itself extraordinary. For billions of years, Earth's habitability was maintained by unconscious processes: gravity, chemistry, biology, operating without any intention or awareness. Now, for the first time, a conscious species has the knowledge and the power to either preserve or destroy the habitability of the world. This is an extraordinary responsibility. We are the first species capable of understanding the conditions that allow habitability, and the first species capable of deliberately choosing to preserve those conditions or ignore them. The philosophical implications are profound. We are not merely inhabitants of Earth. We are guardians of habitability. We are the universe's way of becoming aware of the conditions necessary for its own existence. Our ancestors evolved on this exceptional world, protected by the other planets, maintained in stability by gravity and chemistry. They developed consciousness, curiosity, the ability to understand. We inherited that consciousness, that curiosity. Now we have the knowledge to understand how extraordinary the world we inhabit truly is.
And with that knowledge comes the responsibility to preserve it. The other planets cannot help us now. Jupiter cannot protect us from climate change. The Moon cannot stabilize a climate that we have destabilized. We are on our own. The question before us is whether we will use our consciousness, our intelligence, our unique capacity for foresight and planning to preserve the habitability of Earth for future generations. 32. The Cosmic Alliance. Understanding our place in the solar system. Throughout this journey, we have explored how the planets of the solar system work together to maintain conditions suitable for life on Earth. We have seen how Jupiter protects us from asteroid impacts, how Saturn maintains resonances that stabilize Earth's orbit, how the Moon stabilizes Earth's axial tilt and creates life-sustaining tides, how Mars and Venus and Mercury define the boundaries of the habitable zone, how the Sun provides the energy that powers all life. We have discovered that Earth's habitability is not a property of Earth alone. It is a property of the entire solar system working in coordination. We live not merely on a habitable planet, but in a habitable system, a system where all components function together to create and maintain the conditions that allow consciousness to emerge. This realization transforms our understanding of what it means to live on Earth. We are not merely inhabitants of a globe of rock and water floating in space. We are participants in a cosmic alliance, a partnership of celestial bodies that has persisted for 4.6 billion years. This alliance began with the formation of the solar system from a collapsing cloud of gas and dust. It continued through the violent early history, the collisions of planetary embryos, the late heavy bombardment, the chaotic dance of gravitational interactions. It has been maintained through billions of years of stable orbits and predictable cycles. The alliance persists in the form of resonances between planetary orbits, in the protective effects of Jupiter's gravity, in the Moon's steady pull on Earth's tides, in the Milankovitch cycles that shape climate variations. These are not conscious agreements. They are the inevitable consequences of physics and gravity. Yet the result is a system that functions like an organism, with each part contributing to the maintenance of conditions suitable for life. What is remarkable is that this alliance was not inevitable. The solar system might have formed differently. Jupiter might have remained in a different orbit. Saturn might have migrated farther out or been ejected from the system entirely. The Moon might never have formed if Theia had collided with Earth at a different angle. Earth might have been positioned farther from or closer to the Sun. The asteroid belt might have been more densely populated, subjecting Earth to higher bombardment rates. Any of these variations would have altered the habitability of Earth. Yet the solar system evolved into the specific configuration that we observe, a configuration that is exceptionally suitable for life. The improbability is staggering, and yet here we are, conscious beings, able to recognize and appreciate this improbability. The Cosmic Alliance suggests that we should think of ourselves not as isolated inhabitants of a single world, but as members of a solar system-wide community. Every planet, every moon, every
Asteroid plays a role in maintaining the conditions that allow us to exist. We should think of ourselves as connected to the entire system. When we preserve the habitats of Earth, we are honoring the work done by 4.6 billion years of cosmic evolution. When we damage the climate or destroy ecosystems, we are breaking a link in a chain that extends back billions of years and forward to countless future generations. This perspective can inspire a sense of stewardship and responsibility. We are not merely preserving our own world. We are preserving a world that has been maintained in habitability through the efforts of the entire solar system. Looking forward, the Cosmic Alliance gives us reason for hope. The same processes that have maintained Earth's habitability for billions of years will continue to operate into the future. Jupiter will continue to sweep away threatening asteroids. The Moon will continue to stabilize our axial tilt. The other planets will continue to define the boundaries of the habitable zone.
These protections are not dependent on our actions. They will persist. But this does not mean we can be passive. The protections offered by the other planets are necessary, but not sufficient. They protect us from external threats, from cosmic hazards beyond our control. But they do not protect us from ourselves. Climate change, pollution, habitat destruction. These are internal threats, threats that we create. We must address these threats through our own conscious choices and actions. The Cosmic Alliance has given us a habitable world. Now we must choose to preserve it.
33. The temporal gift. Billions of years to flourish. When you contemplate the age of Earth, when you try to grasp what 4.6 billion years truly means, it is almost impossible to form a mental image. A billion is an almost incomprehensible number. If you were to count to 1 billion at a rate of 1 number per second, without sleeping or eating, it would take you approximately 32 years to finish counting. Now multiply that by 4.6. The human mind cannot truly grasp such scales. Yet this is the span of time that life has had to evolve, to develop from the simplest single-celled organisms to the staggering diversity we see today. Evolution is an extraordinarily slow process. It works through tiny changes accumulated over countless generations. For major evolutionary innovations to occur, for fish to develop limbs and walk onto land, for reptiles to develop feathers and become birds, for mammals to develop intelligence and consciousness, billions of years are required. Consider the timeline of life on Earth. For the first 600 million years after Earth's formation, the late heavy bombardment continued. Impacts were frequent enough to boil away the oceans repeatedly. Yet during this hostile period, life apparently emerged. The earliest evidence of life dates to approximately 3.8 to 3.7 billion years ago, just 800 million years after Earth's formation. Life emerged during chaos, in the midst of bombardment, in the depths of oceans and the pores of rocks. This is testament to the robustness of the chemistry of life, and to the conditions that allowed life to persist despite the violence. From this earliest life, all subsequent life has descended. Simple, single-celled organisms diversified into bacteria, archaea, and the precursors of eukaryotic cells. For the first 2 billion years of life's existence on Earth, from approximately 3.8 billion years ago to 1.8 billion years ago, all life was microscopic. No multicellular organism existed. The planet was a world of bacteria and simple protists. Then, approximately 1.8 billion years ago, the first eukaryotic cells evolved. Cells with a nucleus, with organelles, with greater complexity. For another billion years, eukaryotic cells existed only as single-celled organisms. But then, approximately 800 million years ago, multicellular life emerged. At first, these multicellular organisms were soft-bodied creatures like sponges and jellyfish. They left almost no fossil record. Then, approximately 600 million years ago, more diverse multicellular life flourished in the oceans. Trilobites, early arthropods, early fish. And then, approximately 500 million years ago, fish developed jaws and became more mobile predators. Some of these fish developed the capacity to breathe air and walk on land. Approximately 475 million years ago, the first land plants evolved. Plants colonized the land and created the possibility of terrestrial ecosystems. Insects, arthropods, then vertebrates invaded the land as well. Dinosaurs evolved and dominated for 150 million years. Then, 66 million years ago, an asteroid impact drove many of them to extinction. But birds survived, and mammals flourished. Primates evolved, apes evolved, humans evolved. The entire evolutionary journey from the first simple cells to humans spans 3.8 billion years. But the time allocation is very uneven. Life spent nearly 3 billion years as single-celled organisms. It took another billion years to develop multicellular forms,
It took hundreds of millions of years for plants and animals to develop complex forms. It took tens of millions of years for primates and early hominins to evolve. And it took only a few million years, perhaps 3 to 4 million years, for the genus Homo to evolve from our ape ancestors. Modern humans, with our current level of intelligence, have existed for perhaps 300,000 years. Civilization and written history span only the last 5,000 years. When you place this in perspective, when you realize that humans have existed for only 0.000000002% of Earth's history, the brevity of human civilization becomes starkly apparent. Yet this billions of years long temporal gift was essential for us to exist at all. If Earth were younger, if we were in a younger star system, complex life would not have had time to evolve. Intelligence requires not only time for evolution to occur, but also stable conditions over those vast timescales. This is where the role of the other planets becomes crucial. The stability of Earth's orbit, maintained by the other planets through gravitational interactions, has provided the temporal stability necessary for evolution to progress. Predators and prey have co-evolved. Plants and animals have developed increasingly complex relationships. Nervous systems, brains, consciousness have gradually emerged through natural selection. None of this could have occurred if Earth's climate were unstable, if impacts were frequent, if the conditions for habitability were precarious. The other planets have provided not only a habitable world, but a stably habitable world. A world where conditions change slowly enough for life to adapt, where catastrophes are rare enough for evolution to recover. Looking forward, the question of how much longer this temporal gift will endure becomes important. We have already discussed that the Sun will eventually render Earth uninhabitable in approximately 1 to 2 billion years. But even before then, human activity is threatening to destabilize the climate on much shorter timescales. If we trigger severe climate change, we could reduce the habitability of Earth for our own species within centuries or thousands of years. We could reduce the time available for evolution to produce new adaptations to changed conditions. We could reduce the temporal window for civilization to develop the technology to survive and adapt. In other words, we are at risk of squandering the temporal gift that the solar system has provided. The planets have worked
For billions of years to create and maintain conditions suitable for habitability. They have created a stable stage upon which life could flourish and consciousness could emerge. Now, in the last instant of geological time, the last fraction of 1% of Earth's history, humanity has appeared and is threatening to destabilize the very conditions that allowed us to emerge.